Yeah, I guess we're live now. Good. Okay. Great. So today we're going to cover interconnects, which is a really exciting topic actually, because this is something else that can have its own course. You can have multiple semesters studying interconnects, different aspects of it. And then this also clearly has connection with computer networks as well. And we will see some concepts of computer networks and communication networks in general seeping into this topic. Okay, just to remind you, we covered multiprocessing, memory ordering, and cache coherence last week. And if you remember, we talked about in the last lecture, talked about two cache coherence methods. And we did talk about scalability issues, if you remember. I'm not going to go through this again. We talked about Snoopy bus and directory-based methods. These are two fundamentally different ways of implementing cache coherence. And they're both used in existing systems in a more hierarchical manner. And if you think about it, we said that Snoopy bus-based methods or Snoopy cache-based methods require a single point of serialization, usually a bus. And as a result, they're not scalable. So you need some sort of interconnect that can imitate the guarantees of that single point of serialization. And we said that the directory-based methods are actually exactly as scalable as interconnect and the directory storage. They're much more scalable than a bus, basically. At least interconnect is much more scalable than a bus. We talked about the storage, and we had some issues with storage, if you remember, right? Because storage is there, and you have to keep track of things. But we didn't solve the problem fully. I just gave you some solution ideas and directions, because it's a real problem that is a bit hard to solve. But now we're going to talk about interconnects that actually enable scalability in general. And I call this interconnection networks because there are other types of interconnects, as we will see, as you have seen also. A wire is an interconnect, right? A single wire that cables an interconnect, basically. We're not going to talk about any single cable. We're going to talk about specific cables that are inside chips or that connect different computers. But they're not that different from those cables in the end. And these are some readings that we will cover. I will mention some of these. But let's start with some basics, basically. The question is, where is an interconnect used? To connect and communicate between components, basically. That's why that's an interconnect between my computer and that camera right now. But there are many examples, and these are the examples that we will mainly look at because you specialize the interconnect for your purpose, right? And in this case, we're talking about multiprocessors in general. We may look at some specifics, and your interconnect needs to be specialized for the goals that you have in the design of your multiprocessor system, right? So you may connect processors and memories, different memory banks, processors and caches, I/O devices. Basically, you can have any sort of thing, any sort of, let's say, element that can be connected to an interconnection network, such that it can communicate with other elements, right? And this is one example. You can see that this is some sort of multiprocessor. You have CPU, memory, network interface, and the storage. And these are connected to each other through some sort of interconnection network, and they can communicate with each other. This is a multi-computer network in this particular case, right? Okay, this is from a paper that we're going to study. This paper proposed one of the earliest message passing computers called the Cosmic Cube, developed at Caltech in the 1980s. It's a beautiful paper, actually. I would recommend reading it. It's by Chuck Seitz. And basically, interconnects, the point here is interconnects enable communication, but there are many ways of designing an interconnect. So here, this paper basically shows that you have a switching network and you have some storage modules and processors. Basically, this is called storage modules, but you can think of it as memory today, right? It's main memories, and then you have some processors, and then how do they communicate with each other? How does the memory serve the processors in this particular case? I'm not going to read this. Maybe when we get back to it, maybe we'll look at it. And this is another organization, right? You have the processor and the storage is tightly coupled with the processor. And you have many of these. And then you basically form an interconnect, a particular interconnect that's advocated by this paper. It's called a hypercube, actually. This is a three-dimensional hypercube. And you can see that the connection is a bit different from here, right? The switching network doesn't specify what connections you have. But here, you're thinking of storage modules coupled with processing. And if you want to access some other storage module, you need to send a message to some other node, let's say. So this paper argues that this is more of a good fit for a shared memory model. If you think about what we discussed, shared memory versus message passing, this paper argues that this sort of interconnect, this sort of organization, this is also called the dance hall organization. Basically, you have these processors who want to dance with the storage modules, and they have a dance hall in between, and they get to meet each other in some way, right, through the network. Basically, this paper argues that this is it's a good fit for shared memory model, but may not be a good fit for shared memory model for message passing. If you want to do message passing, you want to have local memories that are not visible to other processors, and you basically send messages through these, let's say, specialized links through the hypercube. So we will see this. But you can see that there are different ways of organizing multiprocessors even to begin with, right? Now, as we discussed last time, maybe this is a good fit for enabling message passing better, but programming model is completely independent of the hardware organization underneath, right? You can expose a programming model, shared memory programming model on the programmer, even if your hardware organization looks like this. And there could be good reasons for doing that, right? Maybe you say that I want shared memory programming model. This processor can see any, basically can do a load and store to any of the storage nodes over here. And I partition my storage nodes so that I can get better scalability in the across the different nodes. But what the programmer sees is a global address space across all of those storage nodes or memory nodes. And I can still have this interconnect, basically. So it doesn't matter whether I have a message passing or shared memory programming model. This interconnect and this sort of organization potentially enables better scalability. Right? Here, whereas here it may not be as easy. I don't know. We'll see. Okay, so why is this important? Basically, why is communication or interconnects, why are interconnects in general important? Because it affects us, how you design it affects the scalability and the cost of the system, two important metrics. It also affects performance and energy efficiency, and also affects reliability and security and robustness, as we will also put over here. So basically, how large of a system can you build? How easily can you add more processors? It's very much dependent on what your interconnect over here looks like. Whether it's feasible to build it, basically, how does the wiring work? Can you actually do this wiring on chip, off chip, etc.? If you look at very large supercomputers that are wired, that are connected to each other with wires, you will see that wiring is a huge headache, basically. And a lot of bugs have been caught because people did not wire the computers correctly. So if your interconnect is very, very complicated, so I said it requires a lot of wiring between different processors, you may actually run into potential reliability issues also, right? Because somebody may have miswired. Right? People are today it's people who are wiring these computers actually. Maybe in the future it's going to be robots that are going to put the wires and verify all of that. But today that's how it is. So a very complicated network can actually make your wiring very complex. And you can see it almost here. We'll see a 6-dimensional hypercube later on. It's going to be even more complicated. Okay. Affects performance and energy efficiency clearly because how fast the latency of the network, the bandwidth of the network affects how fast processors, caches, and memory can communicate, how long the latencies are to memory, how much energy is spent on communication. These are all functions of your interconnect, right? And many design choices affect this actually in the interconnect, as we will see. And then it affects reliability, robustness, and security because if your wires are not reliable for some reason, messages may not be delivered right. So, or if fundamentally, if you're building a very large system, you're bound to get some failures just because there's a failure rate in systems. And if your interconnect cannot adapt to those failures, or if your messaging protocol cannot function in the presence of failures, then you may actually run into reliability, security, robustness problems. Any questions? Hopefully these are obvious, right? So this is from another book that I would recommend. This is actually a book written by Bill Daly and Brian Tolles. And the reason I wanted to borrow this part is to show the same example. This is the dance hall configuration. And this is this processor and memory are combined, and then they communicate with each other through the interconnection network. But the real reason I wanted to show this is because this basically shows an example parameters of processor memory interconnection networks. and basically talks about some parameters. It clearly doesn't talk about every parameter, but you can see that there are processor ports, memory ports, peak bandwidth, which is very low compared to today's standards. 8 gigabytes per second is nothing, right? We're talking about 17 years ago, right now when the book was written. Average bandwidth, which is also very low, as you can see. Message latency, message size, traffic patterns. So what kind of traffic patterns can you handle is also important. They say arbitrary here, but some networks may be specialized to handle some sort of traffic patterns, right? Maybe control traffic, for example, over data traffic. Maybe better synchronization traffic, better reduction operations, as we will see. The quality of service in this particular case, they say none. There's no quality of service provided in this particular network. That may or may not be a good choice, as we discussed, right? Probably not a good choice. Reliability, no message loss, with some assumption, and there's some availability. So you can see that an interconnection network is really evaluated with many metrics, as well as there are many parameters. And this is just a very small list of parameters. And if you're interested in more detail, this is a seminal book that talks about interconnection networks in general. And if you were actually had a course on interconnection network, we would use that book because it has 25 chapters, as you can see. And it would be a whole semester. Many topics that we have in this course can be whole semester, as you can see, but we don't have time. So we're going to cover it in only two lectures. Okay, another example that you have seen actually, this is not what we're going to talk about, but you should really be aware that these interconnects are everywhere. I mean, in our lives there are interconnects, right? The roads are also interconnects, and you can apply the similar design principles that we're going to think about to the roads as well. And I think sometimes I wonder if those design principles are really applied in real life. Sometimes we're not very scientific, I think, but anyway. But let's talk about the clock distribution network. This is a network that you saw in digital design and computer architecture, albeit briefly. It was one lecture again, right? It's about timing and verification. Basically, we talked about clock signal arriving non-uniformly late to different parts of a chip. And it causes potential timing issues that you need to keep in mind when you're deciding your clock cycle time, for example. And if you don't take this into account, you may actually run into reliability issues. So the solution, one potential solution to help this problem, is to design the interconnect to equalize the arrival time of the clock signal to all parts of a chip. So you can have a clock generator and you can have one wire. Basically, that wire goes around the chip like this in some way, in some random fashion. And if you do that, then that's not good, because now the clock signal, wherever the clock signal reaches last, we'll see the clock signal later than wherever the clock signal reaches earlier, right? As a result, there's a timing skew. And if these components are somehow communicating with each other, then you will have problems with deciding your clock cycle, clock frequency, as we discussed. So basically, you design a specialized interconnect that communicates the clock signal from where it's generated to different parts of a chip. And this is one example. This is called an H tree. This is a very specialized interconnect. It's a tree, as you can see, right? This is where the clock signal is generated. And then you basically divide the chip into 4 quadrants in this particular case, and basically buffer the clock signal nicely so that hopefully it arrives at this point at the same time it arrives at this point and this point and this point. So basically the time at which the clock signal arrives at any part of a chip is almost equal in this particular case. And this is a commonly used clock tree network. But you can see that even distribution of the clock, a single signal to the entire chip, requires a specialized network. And this network consumes power. This network has some latency, and you need to have some buffering. You need to design it nicely. So I thought it's quite interesting, basically. But again, this is a communication network. You're communicating the clock signal. And this is, recall, if you took digital design and computer architecture, we talked about this, right? Designers must keep clock skew to a minimum, requires intelligent clock network across the chip. And people are actually doing research in this area. You can see that there are H trees, but there are other organizations that people propose for various reasons, which we're not going to go into. And this is also real. This is data from Alpha 21264 processor that shows when the clock arrives. What's the clock skew basically at different parts of a chip? 0 is where the clock is generated. And you can see that there are some peaks that receive the clock after 60 picoseconds. There are some places that receive the clock after around 10 nanoseconds, 10 picoseconds or so. And this is about 25 years ago. So today those numbers are larger. Okay. Any questions? Yes. Exactly, it's possible, yes, certainly. And also we don't know, right? They don't discuss in detail how exactly, it's done in this particular case. You can read the paper for more detail, but I don't think they go into a lot of detail. Yeah, you can certainly do multiple sources of clock guess. Okay, if you're interested, well, this didn't get covered in digital design and computer architecture, but this is the part where we kind of touched into interconnects and digital design and computer architecture. And I wanted to mention this also because timing and verification is such a critical component actually in design, which we don't talk about in this course, right? And you don't do it in your labs also, right? Because your labs are all high level, C level. So, but timing and verification are actually quite important. Okay, so let's jump into interconnection network. I've been motivating kind of and giving you examples, but what we're going to cover is essentially what we see in this slide today. Hopefully we'll cover topologies, routing and algorithms, not all of them, clearly there are many that are proposed, buffering and flow control. And these are the three basic things that define an interconnection network. What is a topology? This specifies the way the network looks like. Maybe switches are wired, thinks about switches too much, but how does your network look like basically? How are your switches wired if you have switches? And this affects everything basically. It affects how you route, where you go from point A to point B, how do you do that? Reliability, throughput, latency, and how easily you can build it. So that's why we're going to start with topology to begin with. And then we're going to talk about routing. This basically defines how does a message get from a source to a destination. And there needs to be an algorithm or a way to do that. And this could be in different ways, as we will see. This could be static, adaptive, it could be a combination, etc. And then the last piece is buffering and flow control. I put them together because they're tightly coupled with each other. Basically, what do we store within the routers and links? Do we store entire packets, parts of a packet? What is the granularity? And how do we throttle during oversubscription? Flow control means basically if your network is loaded, how do you control the flow of packets or messages into your network? And this could be local or global, right? Locally, a buffer may be overloaded. How do you ensure that that buffer doesn't receive more messages? How do you handle that oversubscription base? Does it sound good? Okay. And you can see that, I mean, all of this is applicable to the internet as well, right? So all kinds of networks have these properties, and you can talk about this on the within the context of internet as well, which we're not going to do. Okay, as we said, actually, a lot of these are tightly coupled with each other, but buffering and flow control are especially tightly coupled with the routing strategy because your routing determines how you do your buffering and flow control as well. So this is an area with lots of terminology. So if you read this book that I showed you earlier, you'll see lots of terminology, which I don't necessarily like. So I'll give you some of the terminology so that we can follow the lecture, but it's a bit unfortunate. Well, some of these are easy. These are the easy terminology, let's say. Network interface. This is basically a module that connects endpoints or processors into the network. And why do you have a specialized network interface? Because it decouples your computation from communication, right? You can say, oh, my processor is going to be my network interface. Yes, but then you need to use your processor for that purpose. Specialized network interface enable that decoupling. Link is a bundle of wires that carry a signal. It could be a single wire also. Switch or router connects fixed number of input channels to a fixed number of output channels. And then it gets to it's connected to a link, and we will see examples. And channel is a single logical connection between routers and switches. Again, you don't need to memorize all of this. I think it's best to learn by seeing examples of what these look like. But before that, I will throw more terminology at you. Node is essentially a router or switch within a network. Message is the unit of transfer from the perspective of the endpoints, let's say clients of the network, processors and memory. They send messages to each other, and these messages are divided into packets, which is essentially the unit of transfer for the network, which is also divided into flits. This is an interesting term, flow control digit. This is the unit of flow control within the network. Basically, packet is unit of transfer, flit is unit of flow control, and potentially buffering. Right? Your buffering can be done at a granularity that's smaller than a packet, and your packets can be smaller than your messages. That doesn't have to be the case. All of these may be equal, right? Depending on what the network is. But for example, if your cache block is 512 bytes, your message is 512 bytes. Your memory needs to communicate 512 bytes to your processor. And unit of transfer, maybe, I don't know, 64 bits in each bus. So you divide that into 64-bit packets. But the flow control may be done in a smaller granularity for, I don't know, for whatever purposes we will see later on. Does that make sense? Basically, you can have different granularities. There's more terminology, direct or indirect networks. These are basically different in the sense that endpoints sit inside or outside the network. Endpoints are clients that communicate essentially. Let's look at an example. So this is an indirect network, for example. You have, assume that these are processors, assume that these are memory banks. You want to communicate between processors and memory banks. And in the middle, you have a bunch of switches, a network basically. This is a butterfly in this particular case. It has this butterfly shape, as you can see. But basically, in this case, it's indirect because the middle switches are also not endpoints, right? There's no processor or memory bank inside these switches. They're just switches. Their purpose or sole purpose of existence is to enable communication between these endpoints and these endpoints. Right? Whereas this is a bit different, right? Now we have actually processors and memory, whatever those are, these green ones. It could be processors and memory, or it could be processors or memory. But basically, these switches are associated with processors and memory. Essentially, endpoints are integrated with the switches also. So there's no special switch that whose sole purpose of existence is just switching, right? Make sense? Okay. And you clearly can have a combination. So you may have some of these just switches, right? For whatever reason, right? There could be a good reason to do that also. You may want to specialize, for example, for some of the nodes over here. All nodes don't have to be exactly the same, right? That's another point over here. We have a lot of accelerators today, and all nodes don't have to look exactly the same over here. Okay. Basically, switch is also called a router. And in this case, you have a radix of 2. I'm throwing more terminology at you, basically, which means that it has 2 inputs and 2 outputs, as you can see. And these networks are usually called like radix array, meaning in this case, it's a 2-array router. Yeah, whatever. I don't know why people develop this terminology necessarily. I think there's good reason to develop it, but sometimes they went a bit overboard. Maybe they didn't want to say radix of 2, basically. Maybe that felt too long, so they said 2-array. So in this case, in this particular mesh, I should say this particular mesh is direct. Every node is both endpoint and switch. Okay, so hopefully we've gotten over some terminology. We'll see some more, but let's jump into topology now. We're going to cover topology, routing, and buffering and flow control. Okay, now I'm throwing more terminology at you. So topology is actually interesting because topology can be regular or irregular, right? Regular examples we have kind of seen over here, but irregular means there's no pattern that you can distinguish, right, in the network. I mean, internet could be one example of that network, right? It's quite irregular. Routing distance is number of links or hops along a route. And diameter is the maximum routing distance within the network. This basically bounds the maximum latency. Basically, maximum number of hops or links that you need to traverse to get from one point to another point in the network. And average distance is average number of hops across all valid routes. So you can basically examine a topology independently of the access pattern. And these are independent of the access pattern, right? You look at this picture, this graph, regular or irregular. You can compute the routing distance. It may be easy or hard, depending on what kind of graph it is. You can compute the diameter, maximum routing distance, and you can compute this, right? I mean, this average distance is basically for all paths. You figure out what is all possible communication paths in the network and get the average distance, because you know the routing distance, you know the distance between any given point A and point B, and average it out, right? Could be interesting, I don't know. It could be interesting for a pattern, a communication pattern where all nodes communicate with each other with a random probability, right? It's also called uniform random communication, which is now we're getting into some access pattern, right? Uniform random is one access pattern or communication pattern that could be interesting, but it could also not be interesting, right? Depending on your application. Which applications communicate uniform randomly with each other? You have 1,000 different nodes, and assume that all of them are processors, and any given pair communicates with equal frequency with any other given pair. That's the uniform random traffic pattern, basically. May or may not be realistic. Usually it's not realistic, right? But sometimes in a lot of papers that's used to judge, let's say, the performance of a network. Not necessarily great. If you're running an application that never sees a uniform random pattern, why do you care about the uniform random pattern? And why do you care about the average distance, for example? Yeah. So bisection bandwidth, you will also see this terminology. I'm going to just define it quickly, but this is used to describe network performance. What you do is you cut the network in half and sum the bandwidth of the links that you cut through or sever. You can also think of it that way. Minimum number of channels spanning the two halves times the bandwidth of each channel. Of course, this is only meaningful if you're cutting it in half, and where you cut it in half is representative of other parts of the network. Right? So if what you're cutting in half is the bottleneck portion, then yeah, maybe that's not good, right? Or if basically if the topology is recursive, this makes sense. But this can be misleading because it doesn't account for many things in the network, and certainly not execution time. So we're going to make an argument for execution time later on. But these metrics are interesting, but they're not necessarily conclusive in terms of the performance of a network. There's also another terminology I will throw at you, which I don't necessarily like, but yeah, it's interesting to think about. Basically, if connecting any permutation of sources and destinations is possible, the network is called non-blocking. Otherwise, network is blocking. And then there's a rearrangeable non-blocking, which you can rearrange the connections when switching from one permutation to another. That enables you to become non-blocking. Fine. Okay, now let's go into the interesting part. Topology. So people have developed a lot of topologies, and they keep developing more topologies. We will see more topologies hopefully tomorrow on-chip networks, because on-chip networks actually enable even more topologies because your wiring is very dense on a chip, and you're not as limited by the cabling requirements, for example, outside a chip. And the wires are much more efficient on chip, if you think about it. Whereas these wires are really not efficient outside here. A wire that I have on chip is like orders of magnitude more efficient than this wire over here. Okay, but on chip, off chip doesn't matter. These are some of the topologies that we're going to look at. It doesn't cover everything. Let's start with bus, and we're going to, this bus is essentially a wire, right? And then we're going to go into other things. But before we go into it, there are metrics to evaluate the topology, which is cost. We're going to talk about several of these: cost, latency, and contention. But keep in mind that there are other metrics also: energy, bandwidth, overall system performance. How is it? How does it support different kinds of access patterns, for example? So basically, you can come up with many other metrics, and reliability potentially as well. Right? But we're going to look at these three metrics especially to begin with. So bus looks like this. I mean, we've seen this before, right? This is our bus-based multiprocessor for cache coherence, for example, Snoopy cache coherence. In this case, you have 8 nodes connected to it. And all nodes are connected to a single link in the simplest incarnation of a bus, right? And this link has some width, clearly. And this is the example that we saw when we talked about cache coherence for Snoopy cache coherence, right? It was not exactly this picture, but it was a variation of my handwriting based on this picture. So clearly, this is simple and cost-effective for a small number of nodes. And it's very easy to implement coherence because it gives you that single point of serialization immediately, right? Okay, the downsides, as we also briefly talked about, is it's not scalable to a large number of nodes. Why? Because it has limited bandwidth, right? This single bus has limited bandwidth, and its bandwidth doesn't grow with the number of nodes. You keep adding more nodes, and its bandwidth actually reduces. Why does it reduce? Because you have more electrical loading on the bus, and you have to reduce the frequency of it. Otherwise, you will get into reliability issues. So you have a lot more noise if you keep connecting more and more nodes to it. As a result, its scalability is very limited to a small number of nodes. 8 is a reasonable number. If you go to 16, you're pushing it. As a result, even 16 cores today don't have buses, as we will see. They have something called rings, as we will also see. Makes sense? So there are 2 reasons, basically, why it's not scalable. One is the bandwidth is limited to begin with. Whatever transactions per second is limited. And if you keep adding nodes, the amount of bandwidth doesn't scale with the nodes. And the second is electrical loading. Due to electrical loading, if you keep adding nodes, you get reduced frequency. So bandwidth actually reduces as you keep adding nodes, which is not a property that you want. And high contention, so the other issue, which is orthogonal, is really whenever you have high contention, you get fast saturation. For example, processor 0 wants to communicate with processor 7. At the same time, processor 2 wants to communicate with processor 3. At the same time, processor 1 wants to communicate with 4 and 5 and 6. You have to serialize all of those transactions, right? Because you have a single medium. And whenever you're not contented, this may be okay. But when you have high contention, then that serialization affects your latency significantly. Right? Yes. So this sort of communication pattern, it could be cache coherence, right? It. Oh, I see. Yeah, basically there's an arbiter. So I didn't talk about that. That's another point of contention, actually. So there has to be some arbitration mechanism to get access to the bus. We're not going to cover that, unfortunately, but it's going to be very similar to any arbitration mechanism that requires access to a link. So there needs to be, whoever wants to communicate needs to request the bus, and then the bus, there's a centralized structure that gives acknowledgement or negative acknowledgement to whoever it gives the grant signal to. So there may be buffering in that arbiter. So that arbiter also becomes actually a bottleneck in the design. You're absolutely right. So that also causes even more serialization. Yes. Yeah, sure. You can fix them. They don't seem to be working.
Do we care about reliability of both components, or
yeah?
It's just one link, and if it's down, the entire system is
exactly.
down.
Yeah, exactly.
So reliable. Do they care about that, or?
Well, don't really care is a strong word, right? You never know what kind of fault you will see. But yes, in general, we do care about reliability. You can make the wires much larger, right? To reduce the probability of failure. But yes, if this single link fails, then you're done in this particular case, right? If a particular wire, for example, fails, it's not communicating, then throw that multiprocessor. Yeah, I mean, you can have redundant buses, but basically this topology is actually not very robust, absolutely. So what we have a name for it that I will introduce later on. It's called path diversity. Basically, in this particular case, there's no path diversity in the network. There's only one link, and everybody has to go through that path, right? There's only one path to go through. But some other network have very large path diversity, meaning that if one link fails, you're okay. You can route around it, basically. There are many ways of getting from one location to another, basically. But that's a very good point, yes. So we could keep adding metrics in this particular case, but reliability is a good one. Okay, so bus, hopefully we agree that buses are not scalable. This is the exact opposite. This is a point-to-point connection. We have again, same 8 processors. And basically, we provide a specialized link for every possible connection. Every node is connected to every other with direct or isolated links. And you keep adding this. And this sounds good, right? Now it's lowest contention, potentially. Well, lowest contention because if 0 and 7 are communicating and 4 and 3 are communicating, that communication can be done in parallel, right? But now you lost the serialization effect, right? How do you do coherence or Snoopy cache coherence at least is an issue over here. Directory is very nice for this actually. If you have a directory-based cache coherence, this is perfectly fine, right? You distribute your directory across all of those nodes and you send your messages in these specialized links. So potentially this could also be lowest latency clearly but some of the links are much longer potentially, right? So with 8 processors, maybe it's okay. Think about 100,000 processors. It's not going to be very scalable, right? So this is actually quite ideal if cost and scalability are not issues. But yeah, clearly that's issues. Those are issues, right? So you basically have cost in terms of connections and ports per node. Every node needs to have one single port, at least one port. In this case, one port to every other node, right? And then you have a quadratic number of links with the number of nodes. Makes sense, right? And this is not scalable. And then, of course, there's the other issue of how do you lay this out on a chip, right? That becomes a problem as well, right? Even with 8 processors, the number of links you have are going to be a lot, and you have to basically juggle through. Clearly, you have some metal layers today in chips, but you have to have a lot of metal layers actually to ensure that everything can go over each other, right? Otherwise, you have to route around different wires, and it becomes a mess basically. So if you can go 3D and every link can be in a different metal layer, that's good, but that's also not scalable because that's expensive. These etching of different metal layers in 3-dimensional space is not that easy. Today, we have around maybe 10, 12 metal layers, okay, if you're lucky. In DRAM, we have close to 2 or 3. But in logic technologies, okay, 10 maybe. But again, you need more than 10 here, right? I didn't do the calculation, but I believe at the worst point, you may actually need more than 10. Go up to, if you don't need more than 10 here, then go up to 16 processors and you will see. Okay. So basically, these are kind of two extremes, like, right, bus and point-to-point. And now we're going to look at things that are in between, let's say. And I will start with something called a crossbar. So crossbar is actually, it solves a problem with the bus, which is concurrent transfers, right? Bus doesn't allow concurrent transfers, but this is still a bit more complex. You could also think of it as, this is an easier way of designing something that looks like this, but maybe not, right? So basically, that's the difficulty of comparing topologies, right? This is a completely different topology, right? You can imagine it and you can implement it, and it looks different. And then you can compare the cost, latency, etc. But in crossbar, every node is connected to every other with a shared link for each destination. So the difference from here is you don't have specialized links right now. You have a specialized link for each destination, right? And every node is still connected to every other because you have a specialized link for every destination. And then each source can actually use that link. But whenever two sources want to use the same link to the same destination, they have to arbitrate. Make sense? So it kind of looks like a bus over here. So this is a single bus that you need to arbitrate for this particular destination. So it's like a per destination bus, if you will. And basically, the good news is now it enables concurrent transfers to non-conflicting destinations. If this processor 7 is communicating with memory 0, this processor 4 can be communicating with memory 7 easily, right? There is no conflict. So you can have 8 concurrent transfers, or as many concurrent transfers as the number of destination links. And it could be cost effective for a small number of nodes again, right? The cost is still n square, as you can see over here. Well, n square in the number of switches, not necessarily, yeah. So, okay, basically this provides you low latency and high throughput, but it's still expensive. The cost is n square still. You can see that the n square links. And it's difficult to arbitrate as n increases. So it becomes like a bus, right? As n increases, because this, if you look at a single column over here, it looks like a bus. It runs into the scalability problems of a bus again, because part of it is like a bus. Does that make sense? So you can actually maybe try to make this more hierarchical, etc. We're going to talk about hierarchy later on, but it's not easy to scale a single crossbar as well. But this is used in some core to cache bank networks because of the contention or lower contention properties, right? Ideally, you would like the lower contention properties of this without the complexity of this, while with the simplicity of a bus. And I think crossbar is somewhere in the middle. Okay, so basically, even some chip multiprocessors have this today, but we will see some examples of more scalable. Because these older processors have had fewer cores, they were able to do it. And I'll give you an example. But this is another crossbar design. You can think of it this way. And we're going to see examples of it. Basically, there's some arbitration that you need to do. These are actual switches, and the control of these tri-state buffers. Basically, tri-state buffers, if you remember from digital design and computer architecture, that's a tri-state buffer enables connection between this and this, let's say this row and this column. And an arbiter needs to ensure that only one of them is enabled and remaining 7 is not enabled. This is arbitration, for example, that we discussed earlier. That's one arbitration mechanism. Who does that arbitration? And there needs to be some specialized structure, basically, that enables that arbitration over here that's not shown. If you read some of the papers that are written, you will see that arbiter. But this is an example. This is Sun Ultra Spark T2, one of the earlier multi-core processors. And you can see that there's a core. There are 8 cores over here, and I think there are 8 cache banks plus a non-cacheable unit. So they have an 8 to 9 crossbar, and this crossbar actually requires a pipeline. Basically, whenever you put out a request, there's a four-stage pipeline that your request needs to go through. First of all, there's a request stage. You inject the request into the pipeline, and there's an arbitration stage, and then there's a selection stage. So arbitration is divided into 2 cycles, basically. And then once you're selected, you can transmit your request. So you can see that there are 2 buffers or 2 deep queues for each requester to hold data transfer requests. So basically, arbitration is not simple, as you can see, and they have a picture of an example arbiter over here. You put out your at most 2 requests over here, and then the arbitration grants only one of them, or only one request from any given requester. And you have the opposite over here also. You have another crossbar going from banks and memory to the cores. Makes sense, right? Yeah, I mean, you can go into the design of this, and maybe the next lab, which doesn't exist, could be making your multi-core system more network on chip based, but it doesn't exist, unfortunately, because we don't have time. But you can see that this crossbar is actually quite large. This is the real die picture of UltraSpark T2. And they call it crossbar, but I believe actually some of these over here are also related to the crossbar. So you can see that this occupies a lot of space in real systems. And we will see rings later, they also occupy a lot of space. And over time, actually, the logic scales, whatever logic you implement in the core scale, but these interconnects don't scale. Again, we know how to scale transistors really well, but these interconnects don't scale. So these interconnects will keep occupying even more of the space. Okay, so let me quickly talk about bufferless and buffered crossbars. We're going to talk about buffering, but it's good to talk about it over here. So your crossbar can be completely bufferless, right? In this particular case, they had buffers, but you don't have to have buffers. As long as you're an arbiter, let's assume that these different network interfaces may want to inject. They just need to arbitrate somehow, and only one of them gets granted this column link, let's say. As long as you ensure that, you don't need any buffering. Right? Every cycle, so basically every cycle they arbitrate, and one of them gets the link, and they get serialized. This is very similar to a bus. Again. So you don't need buffering in the crossbar necessarily. But you can also have buffering, which is similar to the earlier example in UltraSpark T2 that we saw. You basically inject packets, and buffering happens in this output arbiter over here. So you request the link, and once now you need to manage the buffers. Basically, if your buffer is getting close to full, you should not send some request into the buffer, right? So basically, buffering actually helps the arbitration and scheduling a little bit, because you're doing the arbitration closer to the links over here, as opposed to somehow magically somewhere. And you schedule only from the head of the buffer. So it basically cleans up how you do the arbitration. It's efficient support. It enables efficient support for variable size packets also. So how do you send variable size packets if you don't have buffering? You can do it again, but with buffers, you can actually chunk it into smaller pieces and then send them. But now you require n-square buffers, right? That's the downside. And this is actually complicated. And not only just the buffers, but also the buffer management mechanisms, which is the flow control mechanisms over here. Now, bufferless also requires some flow control, but it's integrated into the arbitration, right? Arbitration says, oh, you didn't get it, so don't send anything, basically. Here, you need to manage the buffers separately. Again, it's integrated into the arbitration, you could argue, but the buffers need to be managed. So this is going to be much more interesting when we actually talk about flow control and buffering in non-crossbars, in a mesh, for example. And this buffering cost is going to be significant over there. So we're going to talk a lot about bufferless routing, bufferless deflecting requests. But let's talk about it when we get to it. Any questions here? So these are some example design choices that I'm talking about. We will see more of this bufferless and buffer design choice later. Okay, so that's crossbar. Crossbar is still expensive and not so scalable, right? Then the question becomes, yet can we get lower cost than a crossbar? Can we have a network that's lower cost than a crossbar? Yet we still want the much lower contention compared to a bus, right? We don't want to degrade to a bus, clearly. And this brings us into the idea of multi-stage networks. And this is one example of it. Basically, these networks were initially developed for processor memory interconnections, basically. And they're usually used for processor memory interconnections in supercomputers. They're indirect networks with multiple layers of switches. So you can see the switches over here. These are the intermediate switches. Well, I don't know why we don't have 8 over here. Okay, somehow okay, there are 8 over here, sorry. Yeah, there are 8 processors over here. What is that sound over there? Something doesn't sound very good. Maybe you can open that window instead of this one. Yes, you have a question or? Okay. Okay. So basically you have 8 processors over here and 8 memory nodes. And you can see that there are 3 levels of switches in this particular network because each switch is 2 by 2. And these are indirect networks because these switches are the sole purpose of the existence of those switches is just switching, right? They're not processors, they're not memory. Their goal is to switch. And their goal is what we said earlier. Lower cost than a crossbar, still low contention properties. Okay, so this is one example. It's called an omega network. There are many variations of this. Now your cost is not n squared anymore, right? Your cost is really n log n. You can do the calculation because you have 3 levels and you have n in each level, right? And the number of levels that you need to have is really log n, assuming that you have equal number of processors and memory. 64, 64, then it's 6 levels. If you have 256, that's 8 levels, right? Of course, it depends on what your switches look like, right? If it's 2 by 2 switches, it gives you 8 level. If you do 4 by 4, then you're going to get some different number of levels. Right? Okay, and latency is log n, as you can see. And many variations. We're not going to examine the properties of those different variations, but it's certainly interesting. Does that make sense? And you can perhaps see why this is lower contention than a bus, right? Because there are multiple paths right now. Yes.
So are those each of those binary numbers on a given side, a separate processor or a channel of the processor?
Yeah, you can think of this as there are 8 processors and there are 8 memory banks over here. Yeah, initially this was developed for that purpose.
Okay, yeah. Maybe it was what you said earlier, but I don't see how that's n interconnects per layer. It looks like n over 2 interconnects per layer.
Well, n is this is a big O notation, right? N over 2 is just half is just a constant, right? Sure. Okay. Yes.
Right.
Yes, yes, you have to go through multiple switches. That's right. Yeah. That's right, exactly, yes. So there is a trade-off that you're doing, which is you have increased latency to get to the memory banks. But it's lower cost than a crossbar. Yes.
Now these switches would need some kind of logic or controller in them to route incoming packets.
That's correct, yes. We'll talk about that later on, but yes, there needs to be some routing mechanism that basically decides where the incoming packet should go. Okay, so let's take a look at an example. Assume that processor 7 wants to communicate with memory 7. This is the path that you have to follow, right? And assume that at the same time, processor 1 needs to communicate with memory 6, even though they're not communicating with the exact same memories, they conflict with each other, right? So there's a path conflict over here. And as a result, this needs to be handled by the switch. It could be handled by buffering. It could be handled by some other way. We will see. But basically, this is, you can see that you get conflicts compared to a crossbar in this case, right? But you're lower cost than a crossbar, clearly. And you're better off than a bus because this is a bad case that I'm showing you over here. If processor 0 is communicating with memory 0, that's good. They can do it, right? Okay. You can think about whether this is blocking or non-blocking for yourself. I'm not a fan of those questions, but it's good to think about it. Okay, so basically these are multi-stage networks. They're also called logarithmic networks. They're also called multi-stage logarithmic networks. They're logarithmic because you can see that cost and latency grow with log n, right? Basically, you have more restrictions on feasible concurrent transaction and requester pairs compared to a crossbar, but you're more scalable than a crossbar. It depends on the network, of course, but for Butterfly and Omega, a lot of the networks, it's O and log n. But you're constructing a network using crossbars, right? So if you think about each switch, it can be a 2 by 2 crossbar, right, internally. And each switch can be actually a network by itself. If your crossbar, if the crossbar here needs to be 8 by 8, maybe internally it's a network, right? So you can actually construct a network with components that are themselves networks internally. So think about that. 2 by 2 is the simplest crossbar you can build, right? So 2 by 2 is a good crossbar to build. You don't need to construct it with a different network. But if you want to scale up this crossbar to 8 by 8, for whatever reason, we will see later when we build a mesh topology, we may need 5 by 5 crossbars or 4 by 4 at least. Then that crossbar becomes complicated by itself. And if you want to reduce the cost, you may want to apply some of the ideas that we're now thinking about. Build the crossbar or whatever it's called. It's not a crossbar anymore, of course. We build a switch with some other topology than a crossbar. Does that make sense? Yeah. So switches, basically, internally, the switches can have their own topology. Okay. Okay, what am I? So this is another butterfly over here. We will see other examples. You don't need to know exactly what these networks are because there's so many of them, actually. We're not going to cover all of them. But I will mention one thing with these multi-stage networks that's going to be applicable to other topologies also. So now you need to route the messages, right? You need to route, basically the routers need to have some information so that you can go from 0 to any particular node, right? So, which was not the case in crossbar, for example. Then you need to arbitrate. But here now your switches need to be a little bit more intelligent, as you said. They need to have some logic to enable routing. The question is, how do you do that routing? But basically, there are two approaches to this. One is you can be circuit switched. Have people learned about circuit switching versus packet switching in the past? Okay. You've taken a computer networks course, I assume? Okay, yeah. Who has not learned about circuit and packet switching? It's fine. Okay. So you haven't taken a computer networks course, probably. So basically, there are two approaches to switching. Circuit switching says that whenever you want to communicate between source and destination, you first set up the routers such that routers ensure that there's a path basically that gets set up completely. Switches are configured completely so that the data can go nicely from those switches. Basically, you have a phase where you set up the switches such that you can communicate between 0 and 6, for example. And during that phase, this router is configured such that it communicates 0 to the bottom output. This router is configured so that it communicates the top output to the bottom output. And then this router is configured such that it communicates the top output to the top input to the top output, right? So you have this phase where the switches are set up. And then you can send the message because the switches are completely set up, right? There's no need to individually decide for a packet where the packet needs to go because you set up the path before you made the transmission. Does that make sense? Yeah, so this is called a circuit, basically. You set up the circuit. You kind of configure the circuit such that 0 can communicate with 6. It's also called pre-configuration, basically. You pre-configure the switches. And then the good news is there's no need for buffering in this particular case, right? Because switching is static once the path is set up. Every router knows exactly what to do because you set up the routers. And this could be using configurable logic, for example. This could be using some configuration registers in the crossbar. Every router knows exactly what to do. And it looks kind of like a full wire, right? If you think about it. There's no need for really buffering in this particular case, as long as you can afford the transmission and timing works out nicely, right? So basically, from the perspective of node 0 and node 6, the data can basically flow through the setup switches. It's like kind of like a single wire. I like thinking of it, abstracting it that way, right? And ideally, it should be like a single wire. So basically, you can get rid of buffering. Does that make sense? Now, there's a downside, of course, clearly, hopefully, obviously. While 0 is communicating with 6, nobody else can use those routers, right? Does that make sense? Because the routers are set up that way. I guess you can kind of play tricks such that, yeah, I guess nobody else can use those routers, sorry. Yeah, exactly. So some other communication can potentially happen. For example, this could happen. As long as the paths are not conflicting with each other, there's still communication, concurrent communication that can happen even in circuit switching, right? For example, 7 can communicate with 5 because they don't share any common router, right? So circuit switching still enables some concurrency of communication, but not perfect because you're not utilizing all of your switches in the best way possible. For example, while 0 is communicating with 7, I know no one can communicate with 6, right, or 7 in this particular case. And some intermediate router also that you have to go through is busy now because it's dedicated to this communication. As a result, no one can go through that router. Yes.
So why can our switches, which are supposed to be 2x2 crossbars, why can they not serve different inputs and outputs at the same time?
Well, that's because this is the method we're switching. That's because this is circuit switched. But if you're packet switched, yes, they can certainly do it. Maybe I'm misunderstanding your question, but
So
basically you're forming a path and you're dedicating that path to that communication.
yeah, exactly. So that's my understanding of circuit switching. But my understanding of circuit switching would then also be that one crossbar is perfectly happy to be switched for 2 distinct paths at the same time.
You can do that. Yeah, I mean, now you're enhancing your circuit switch, right? Yeah. So basically, I think what you're saying is, so I see what you mean, basically. Yes. Yes, in the more strict sense of circuit switching, you cannot do that. But yes, potentially, you can say, yeah, but that requires now conflict resolution, right? Does that make sense? It depends on how your crossbar is potentially implemented internally as well, right? If your crossbar is, so potentially you can support communication from 0 to bottom here and 1 to top here. Yes, but it depends on how your crossbar is internally implemented. If there's some conflict because they've designed the crossbar such that that communication, it's simple, right? Then that may not be possible. But there can be cases where that is possible, right? Sure, because you can exploit the internal wiring inside the crossbar.
I see, thanks.
Yeah, that's a very good point. Basically, there's internal parallelism inside these crossbars that can enable that communication. I was not assuming that internal parallelism inside the crossbars. Okay. But at some point, that parallelism is limited, right? So at some point, you will still be contended. Yes.
In circuit switch networks, what happens when 2 nodes request the same destination? So there's 5 and 7 both request for 7.
Yeah.
And then let's say one of them gets through.
Yeah, exactly.
So what does the other one get feedback that it couldn't get through?
Exactly,
So it just
yeah.
keeps retrying to the camp?
Yeah, there exactly. I mean, there are multiple approaches to congestion control also, right? You could potentially, well, you don't have buffering in this philosophy, so you basically get a NAC, negative acknowledgement, saying that you didn't get the circuit, try again at some point. Yeah. So there is overhead for that path setup, basically. Setup and connection setup and tear down definitely require some overhead for sure. And then there are latency overheads also. Yeah. Packet switch, on the other hand, is fully flexible. Basically, each router decides the route based on the packets it receives, right? And every cycle, potentially, you can make a complete different decision. Packets hop from router to router, pending the availability of the next required switch and buffer. This is a buffered packet switched example. But basically, there's no path setup. If you have a packet that comes to the top over here, that comes to the bottom, that wants to go to the bottom. And if you have another packet that comes to the bottom of here and that wants to go to the top, or that wants to go to the bottom also, then you basically arbitrate, and one of them goes through and the other gets buffered, for example. Right? That's the idea. So you make the decisions on a packet-to-packet basis as opposed to flow basis, right? Here, you're making routing decisions based on a flow basis. You set up the flow, and as long as the flow is communicating, conflicting flows cannot communicate, let's say, in the strictest sense. Whereas here, you don't have the notion of a flow from the perspective of the router. Each router makes a decision on a packet-by-packet basis. Okay, so let's talk about the downsides and upsides, right? Clearly, circuit switching sets up the full path before transmission, packet switching routes per packet in each router. And we've obviously discussed this. Okay, we already discussed this also. So clearly with packet switching, because you're routing each packet individually, if the link is free, any packet can use it, right? Whereas with circuit switching, if the link is free, any packet may not be able to use it. With circuit switching, you get faster arbitration, clearly, right? Because once you set up the path, there is no arbitration, actually. There should be no arbitration, ideally. No buffering, ideally again. But setting up and bringing down the path takes time. With packet switching, this is potentially slower because you might dynamically make a decision every time you receive a packet. And that takes time compared to making no decision, right? Once the path is set up. And there's need for buffering in general, or some sort of control of the flow. Whereas once the circuit is set up, there's no need for flow control, for example, in the circuit switching rate. But the downside, the big downside, the big upside of packet switching is there's no setup or bring down time, right? You basically send your packet and you start communicating. You don't need to wait until the path is formed. Okay. And it's maybe even more importantly, potentially, it's more flexible. It doesn't underutilize the links, right? So if you look at circuit switching, this is actually good for some other patterns as well, right? Ignore conflicts right now. If you want to, for example, communicate a huge stream of data, 1 gigabyte from this 0 to 7, circuit switching is actually quite efficient, right? You basically keep pumping the data and at the granularity of the links, of course, and the data keeps getting transferred to 7 with little delay. So for streaming access patterns, this could actually be quite good. But less streaming access patterns, more arbitrary access patterns are much better supported by packet switching. Okay. And we can talk about more trade-offs, of course, but let's leave it aside. So switching versus yes, please.
Packet switching deal with the potential packages in the other direction. Is there like a separate buffer, or do they share like a single buffer?
Meaning other direction from right to left in this particular. Yeah, exactly. Again, it's a design choice, right? You could potentially share buffers in both directions, but usually it's easier to have separate buffers for the other direction. Yeah, people have looked at buffering internally in a router, for example. You can have a global buffer for everything potentially, right? And that could be your memory, and you could use that to distribute packets. But those global solutions are usually not very scalable. Usually you have per input buffers, per output buffers, or both per input and per output buffers. Yeah, yes.
You said that so circuit switch is sort of like pre-configuring the switches. That sort of means you have to have a size n squared times log n lookup table, where you would say for the connection from 0 to 8, you would activate these 3 switches, for example, right?
Well, that's when you're forming the circuit, right? Yeah, when you're forming the circuit, you need to have some sort of network that enables you to do that, yes. Yeah. Yeah, but it doesn't have to be that bad, right? If you have some other network that enables you to communicate to form the circuits, then you don't need that lookup table, right?
Okay, yeah, I think I was just confused about like when you said that for a circuit switch, you sort of like pre-configure the switches, or like you sort of like configure the circuit, whereas in packet switch, it seems like the implications you don't do that. So I guess I was just curious on what the difference is then, like what that means.
Yeah. Well, it doesn't need to be, the other network doesn't need to be packet switch necessarily, right? It could be a specialized network for connection setup, potentially. It could be a packet switch network also, sure, but it could be a very specialized network that doesn't have that huge cost, O(n) square. I'll let you think about it. Okay. Okay, these are very good questions, actually. And these give you the space of what we're covering right now, actually. There are a lot of design choices, basically, in how you design the network. So, but this is an aside, basically, switching versus topology. Circuit and packet switching choices really independent of the topology. It's really a circuit switching or packet switching is a higher level protocol, how a message gets sent to a destination, right? But some topologies are clearly more amenable to circuit versus packet switching, as we may see later on. And remember, I showed you this picture when we talked about heterogeneity, right? We were talking about interconnection networks a little bit at that time. And you can see that this is the two-dimensional mesh topology, which we will see. And this Tylera processor has 5 networks. And if you remember, we said that 4 of them are packet switched. One of them is circuit switch. So this is used for streaming data that requires low latency and high bandwidth guarantees. And it's called the static network, basically. And static because it's not dynamically switched. Right? You set up the path, maybe with one of the other networks that you already have. That's also, I believe that's how they do it, basically, because they have some packet switch networks. Why not set up the circuit switch path using the packet switch networks? So it may come for free, basically, the packet switch network. And the packet switch networks are also used for other things, right? As you can see, they're specialized for different things. We'll get back to this again, right? Any questions? So basically, you may not have only one network, one type of network in a system, because different networks are there for different purposes, right? Even request versus response networks may be different as well, right? And I think there's a good reason to separate them. Of course, it comes at a cost, right? But you may want to decouple requests from responses. This is higher level implications, potentially deadlocks, for example, right? You may have protocol deadlocks because your requests and responses are reordered with each other in a way that you don't want them to be reordered. And these are some of the not so nice things that may happen in your network. We'll talk about deadlock later. Okay, any questions? Okay, so let me give you some more examples of these multi-stage networks, and then we're going to switch to some other type of topology. But this is one of the earliest forms of multi-stage networks, actually. It's called the Delta network. You can read this paper. It's a seminal paper in the area. This is the same Patel who developed the MESI interconnection network, MESI cache coherence protocol, basically. So you can see that early people were working on many, many different topics. But I mean, what do I want to say over here? This was one of the first networks to propose to replace costly crossbars as processor memory interconnect. And you can see that each router kind of looks different over here. I mean, it's not important here. Omega network is used in this MYU Ultra computer, which is an interesting computer. I'm going to give you another thing that they did in this particular computer. But in this stage, all stages look the same. They're basically symmetric. But it's another network with different properties because of the way switches are wired. But one of the interesting things that they did in this particular network was actually do operations inside the network. Basically, these switches were not just there for communication, but they could also do some simple computations as well. And they call this combining operations. And the idea is to combine multiple operations on a shared memory location. And the reason they wanted to develop was to enable better synchronization across a very large number of processors, right? If a very large number of processors are updating a shared memory location, then why not do this in the network while they're transferring the data from the memory to the processors? That's the idea. So you can have an operation called fetch and add, for example, as we will see. So basically, these switches combine fetch and add operations in this computer. And what's the fetch and add? You're supposed to fetch memory location M, and you return that memory location. Let's assume the value is M. This is actually not very nice. I think it's probably better shown over here. You basically increment that memory location with some I. That's the idea. So you increment the value with some addition value that you provide. So an example where this could be useful is when you're actually synchronizing, when you actually want to get your chunk in a huge array, for example, and each processor is supposed to operate on an array. Array has a beginning, right? And each processor needs to atomically update the index of the array. So you're trying to divide tasks between arrays, and each processor wants to fetch some amount from the array. This could be useful, right? Because everybody's incrementing by some amount. It could be a different amount. The thing that you're synchronizing on, that synchronization variable could be the index, the latest index of the array, for example, for whatever reason. This paper actually shows a lot of other examples too. But the shared variable needs to get updated, and everybody needs to see the value of the shared variable. And the switch basically does that update automatically because it knows what kind of operation that the processor is trying to do. Instead of just sending the data to the processor and the processor doing the update at that point in time, the switch does the update. And if it sees another request to that location, it sends the updated value to that other processor. So that way you can actually do synchronization completely inside the network. Does that make sense? Okay. Yes.
Wouldn't this cause coherence problems? Because all the processors, I mean, it's a multi-stage network, so there are multiple routers. If one router does the update, how does everyone else see the update?
Well, yeah, coherence, ignore coherence. Coherence is satisfied in some other way, right? This is being fetched right now from memory. If it's cached somewhere else, then you already have some coherence problems to begin with. Does that make sense? Yeah, but you need to satisfy coherence. Yes, you're right. But so basically, you should not be updating this value somewhere else if you want to do something like this. Yeah. Okay. So you can also see that, yeah. I would suggest reading this paper, actually. This paper actually has quite good examples like fetch and OR, so that you can do good synchronization across many processors. And this is one of the earliest examples of processing inside the network, I would say. You can clearly offload even more operations, right? They don't have to be shared memory locations. While you're transferring the data, while the data is waiting, coming from memory, why not do the operation over there inside the buffer, right? So there could be other reasons for doing this operation than just synchronization, because you have already this transfer latency between the memory and the processor, and there may be contention. Just do some of the operations while the data is traveling back to the processor. And maybe by the time it comes back to the processor, it didn't need to go back to the processor, right? Because you did all the operations. Okay. Okay, so combining reduced synchronization latency, and this paper shows a lot of data. Well, this is the paper actually. They've written other papers on the topics that show the synchronization benefits. Okay, this is another example. I could keep giving you examples. This is a butterfly. This is also nice, as you can see. So this also helps with some communication patterns, as you can see, right? It depends on how your communication is done. So these people who developed the butterfly, it's used in a computer called BBN Butterfly, saw a lot of contention issues because of the applications they were running. So they were basically seeing this tree saturation that they called it. It's not a great name, I think, but basically they had some saturation problems on some of the links over here. And they did some randomized route selection on the network. We'll talk about randomization a little bit later. Okay, I'll go through this relatively quickly, but we've seen some topologies. We didn't see mesh completely yet, but you can basically evaluate topologies in terms of what they look like, and I'll let you do it. Now we're going to talk about mesh soon. So I think the key over here is cost and latency, right? This was our crossbar. Cost was O(n) squared, latency was O1. By trading off cost and latency, we got to a hopefully better point. Again, it depends on your access span. But this is more scalable because you don't have this issue of a single bus associated with a destination, right? Now you're as scalable as the links that you have over here. And none of the links that you have is loaded by more than the radix of your router, basically, right? Here, you have a lot of loading on this particular bus. That's why crossbar is not scalable. But this is definitely, I would call, much more scalable because your links are very short, right? Make sense? And they're not loaded. They're still point-to-point links, right? Each link goes to only one other point. There's no link that goes to n other points. Okay. Now we're going to look at mesh. Well, before we look at mesh, I think I should introduce rings. I'm kind of navigating the topology space in a different way. So we're kind of here right now. Mesh is going to be interesting. But before we go into mesh, we should also talk about rings because this is another simple topology. Right? And ring essentially looks like this. You have each node is connected to exactly two other nodes, and nodes form a continuous pathway such that packets reach any node. And that's what the ring looks like, basically. And this is cheap. Our cost is now not n log n, for example, O(n). But now we have a higher latency, O(n), right? In some cases, you're lucky because the node that you're communicating with can be right next to you with one link. But in the worst case, it's really O(n), right? And it's not easy to scale this because as you keep adding processors, you're not adding bandwidth, right? Unless you're making a ring wider and wider and higher frequency, but you can do that with any link. So you can see that this is O(n) and O(n) in both cases, right? And you can see the trade-off compared to these other networks. Okay, so this is interesting. And this is actually used in many multi-core processors. Many commercial systems today use it because it's simple, right? And unidirectional ring has a single pathway. you go from, I don't know, left to right in this case. So there's no right to left pathway. It's probably a bad idea, but it's cheaper. And you can see that each ring stop has a router over here, 2x2 crossbar again, in this case, because you have what's on the ring can be ejected, or it could follow the ring. And and the processor or node can inject, as you can see. Yeah, so it's a 2x2 router over here. You could simplify the router clearly, because not all pathways make sense over here. The good news is this is very simple. It's not as bad as a bus. So the problem with the bus was single shared link, right? Now you have no single shared link. It's just point-to-point communication between processors, right? And you get reasonable performance if n is small, and performance needs like bandwidth and latency are still moderately low. And I mean, ignoring the ON notation, average hops is really n/2, right? And latency depends on your utilization in this particular case. Okay, you can think about it. This is simple to analyze. But bidirectional rings make sense because if you're unidirectional and if you're unlucky, you have to communicate between, basically you have to go through n hops to get to the destination, right? But if you're bidirectional, if you have another pathway from left to right in this particular case, well, no, from right to left, right? Yeah, from right to left, then you can actually communicate with one single hop between processor 0 and processor n-1 in this particular case. Right? So basically, bidirectional rings or multi-directional pathways or multiple rings, it reduces latency. It improves scalability because it enables higher bandwidth as well. But now you have slightly more complex injection policy. You can think of this as two rings, right? These two rings do not need to communicate with each other. One goes from left to right, the other goes from right to left. And there really needs to be no communication with each other unless there's some reason for you to do that. But now you need to decide which ring to inject. Do you want to go from left to right or right to left? It depends on, again, multiple things. It could be dependent on the destination, how far it is. It could be dependent on the contention on each of the rings. So there could be multiple reasons, but destination is definitely a good one to think about. Okay, and these are, because of their simplicity, they're used in existing systems. This is the latest Intel processors. And you can see that even these simple rings actually occupy a lot of space. Right? It's actually surprising how much space they occupy, right? Because there needs to be control, there needs to be buffers, and I believe these are actually bidirectional rings in this particular case. Yes. Yes.
Okay, but it still seems like, I mean, what's that like? Probably even a few % of the entire chip just for these rings.
Yeah, exactly. I mean, because these are interconnects, right? I don't know exactly what they do. Of course, they don't disclose everything they do, but you can get sophisticated. Yes.
Yeah, these rings, or I guess the section here allocated to the rings doesn't look that much smaller than the section we saw earlier allocated to a crossbar. So couldn't they, do you think they could have just increased the size of this by like maybe a few % and gotten something that was much, much faster?
I don't know. Yeah, I mean, it's not good to compare these pictures, right, necessarily, because first of all, there's some inherent inaccuracy. What fraction of that is really used for exact rings? And the earlier picture that I showed you was from, I don't know, 16, 17 years ago, right? What happened during those 16, 17 years ago is Moore's law technology scaling. Our transistors became much more efficient, our interconnects did not. So I think you're seeing that effect. Assuming these pictures are perfectly trustworthy, that's the reason for that effect, basically. So if you build a crossbar, it's going to be much bigger than this. I can guarantee you that. In this case, the crossbar needs to be, I don't know how many. So you can see that 1, 2, 3, 4, 5, 10 L3 banks. And I believe they use L3 banks to cores. And I think they may actually have some hierarchy in this particular smaller cores over here. But it's at least, I would guess they have a 10 by, yeah, I would guess they have 10 ring stops. Yeah, I think that's kind of justified over here, right? So you'll have a 10 by 10 crossbar if you have to imitate this one. And that doesn't sound very good. Yes.
In general, like in these connection networks, where does the memory controller and main memory fit in?
Yeah, so that's a good question, basically. I mean, you could have the memory controller as part of the ring stops, right? So basically, you don't have a single interconnection network necessarily also. That's my answer to you. In this particular case, this ring is just communicating between L3 and processors, as far as I know. I'm not sure if it's really communicating to the memory controller. Does anybody know? I guess not. But you could have a separate interconnect that goes to the memory controller, right? But if you want to use the same interconnect so that everything is more modular, etc., then it could be another ring stop, right? At a particular location. Yes.
So if basically the cheapest thing you could come up with is so big on a chip,
Yeah,
like,
yeah.
are we still doing research on this if you cannot even afford to do the simplest thing?
Again, take this with a grain of salt, because we don't know exactly if these blocks are actually dedicated solely to the ring. But yes, I mean, these are expensive structures, right? You have large wires. You have even the 2x2 crossbar is large. So going to 5x5 is expensive. That's why we're going to talk about some research that tries to reduce the complexity of the crossbars, for example. We have done some research. We wanted to get rid of buffering, for example, for especially these reasons, and make the router as simple as possible. Yeah, no question about that. And once you go to more complicated topologies, this network interface will become more complicated. Yes.
If just a regular ring interconnect takes this much, wouldn't it be prohibitively expensive to have like the Omega, even with the routers that have implemented in them?
Yeah, potentially, yeah. But remember, those topologies were developed for a different reason. So these are on chip currently, but those topologies were developed in the 80s, 90s, so that you could do the wiring of multiple processors that are separate from each other. So right now everything is on chip, and I agree, on chip some of those topologies don't make a lot of sense. That's why on chip topologies may need to be a bit different. Yes.
Is there also something like skew?
Say it again. I can.
Is there something similar to the clock skew for a ring? Would we also experience skewing between terminals that are really far away on the ring?
I mean, I don't know what that means, because you're not communicating a single signal here, right? You're really communicating packets in this particular case. You could do circuit switching on this also, sure, yes, but it probably doesn't make a lot of sense. Basically, you're not communicating a single signal.
All right. Yeah. Thanks.
Okay. So how do you scale rings? So rings are actually nice, I think. But any network, any topology, you can scale by building hierarchy into it. So you can have hierarchical buses also. We didn't talk about. You can have hierarchical rings, and these are some examples of hierarchical rings. And I like this topology a lot, actually, because there's a lot of benefits. You can see that you have rings here, and you have a ring connecting them, right? And this ring may have higher bandwidth. It's a fat ring, in a sense. We will see fat trees later on. This higher level ring may have high bandwidth so that you can actually quickly communicate between these different rings. So this is, and you can see this is another way of connecting the same 16 nodes. This could be your second level in the hierarchy, right? This could be, now you have, again, 4 red rings, let's say, and then you can have 2 other rings connecting them in different ways, right? And you can see that this is clearly more scalable, and this gives you more path diversity, as we will discuss also, because now you can communicate locally nicely on this ring, and when you want to communicate from here to here, you hop onto the second level ring. And now you have 2 different rings to hop onto, and here you're adding additional connections so that you can hop on more quickly to the, let's say, global ring. Here you have 2 global rings, right? So it becomes interesting, basically. And this is the 64 node version of it with 3-level hierarchy. You have local rings over here, 4 of them, and you have a second level ring over here, and then you have a global ring over here. So I think this sort of hierarchy actually enables more scalability and also lower latency, because if you had a single ring connecting 16, that's not as fast as actually these 2-level rings, right? here you basically have, let's say 4, and then you go 4, and then basically your latency is lower actually in the worst case over here, and also in the average case. And if you actually have this organization, your latency is even lower because you can more quickly hop onto the global or one of the global rings, and your contention is lower because you have 2 global rings. Of course, this is more complex now, right? It starts becoming more complex. But this is a way to scale, for example. Yes.
How would something like a directory fit into this sort of like hierarchical design?
It would fit nicely, I would say. So you would distribute your directory, for example. It could be any one of these red nodes. And whenever you want to communicate with the directory, you send a message to one of those red nodes, right? So each red node may be a processor as well as the directory, portion of the directory, and then they communicate with each other. Does that make sense? It's all about the routing, basically, how fast you can route at that point, right, to your destination. Okay, so I think this is actually quite nice. I don't have time to talk about it, but these works describe the design implementation of a mostly bufferless hierarchical ring. We're going to talk about routing a little bit later. And if you're interested, actually, we have works in this area that I would recommend. Okay, now let's talk about mesh. So mesh is also interesting. It solves the one problem with like non-hierarchical rings, which is the latency. Basically, each node is connected to 4 neighbors, north, east, south, west. And average latency is square root of n in this particular case. You can see that over here, the worst, yeah. And the cost is O(n). And this is much easier to lay out on a chip because you have regular and equal length links, right? Everything is essentially the same. You stamp out exactly the same node, right? And the router. And the path diversity is very high over here. There are many ways to get from one node to another. That's true for hierarchical rings also, right? The path diversity from going from this node to this node, you can enumerate many paths, right? And if there's a conflict, you can avoid the conflicts by doing the routing nicely, right? That's true for mesh as well. Going from this node to this node, there are many, many paths you can follow, right? With packet switching or circuit switching. And this is used in especially research prototypes. And Tylera is the only commercial system that uses it as far as I know. But their networks are also quite complex, I think. But especially a lot of research prototypes use it. Okay, I mean, this is interesting, clearly. You can do more analysis on mesh, which we're not going to do. But Torus solves one problem with mesh. Mesh is not symmetric on edges. Basically, this poor processor over here has only 2 paths it's connected to, right? So edges, basically, edge routers over here, edge processors, are kind of not, let's say, not nice. So what happens is actually, with a lot of traffic patterns, traffic gets congested in the middle because edge routers have nowhere else to communicate. So the congestion patterns are not very good in mesh because of this lack of symmetry. And Torus solves this problem, basically. And also, performance is very sensitive to placement of task if you have this distinction between edge and middle routers, right? If you're placed on edge, your communication bandwidth is very limited. So Torus solves this problem by adding additional links, which is basically you add a link over here, and you add a link basically to connect the edges on either ends, both left and right, as well as top and bottom, right? And it looks like this, basically. Now it's symmetric, right? So you don't have this issue. So you have even higher path diversity as well and higher bisection bandwidth as well. But now you're higher cost. It's harder to lay out on chip. Now you have kind of unequal link lengths, right? How do you do this one? It kind of looked nice over here. You don't have these irregularities, if you will, right? Yeah. But this is one way of potentially laying out the torus, right? You weave the nodes to make internode latencies kind of constant. So there are potential solutions to it, but again, it's not as regular as you would like it to be. Nothing is as simple as this beautiful mesh, right? Does that make sense? Or layout, I would say. Okay, so let's talk about trees. We've seen the H tree, clock tree, which look like this basically, but this could be also a processor. Processors can be connected this way also. These don't have to be clock signal that we're getting routed somewhere. And this is by nature a planar and hierarchical topology. Latency is essentially a function of the depth of the tree or height of the tree. And this is good for local traffic. If you have communication patterns such that these processors are communicating a lot with each other, that's good. And if they need to communicate with other processors, then they go through this part of the tree. And people have developed fat trees that look like this. As you go to the higher levels of the tree, the bandwidth on those links actually is higher, so that you can actually balance the communication. So if you're communicating a lot between these two nodes, for whatever reason, because these nodes may be communicating with these nodes, having higher bandwidth over here helps. Again, this is relatively cheap, and it's also easy to lay out because it's very regular. And root can become a bottleneck, and that's why fat trees actually avoid this problem. Does that make sense? Okay. So this is very much depend on your communication patterns, right? So if you're adding a large number of numbers, for example, each node can be doing the addition and then passing the results to the top node. That one could be doing the addition and passing the results to the top node. Basically, you can reduce. Trees are very good for reduction operations, where each node does some computation, pass the results, such that that node, the upper node, can do computation based on the results it receives from the, let's say, children. And that way you can reduce the values as you go to the top of the tree. And so it's good for synchronization also. So connection machine, which is actually one of the earlier parallel processors, it was actually bit serial processors. Basically, these people said, we can have many processors, and we don't care about the latency of each operation because we have a lot of parallelism. And each adder in our processor is a bit serial adder. So if you want to do a 32-bit add, you wait for 32 cycles. But this processor was able to do a 64,000 add, so that the latency of each add was not that important. So for scientific applications, they showed that this was actually a pretty good processor. It's a bit ahead of its time. It was developed in the 1980s. But these folks actually had this fat tree, and it looked like this, basically. It's not a simple tree like this. It's more like based on 4x2 switches. So 4 nodes are connected to a switch, which routes things to 2 higher level nodes, right, as you can see. So it's not a binary tree. This probably has a name that's based on this airy definition, but I don't want to do it. But basically, it was packet switched, and it had randomized routing. So it would choose the path in a random way nicely. And it had a lot of operations inside the hardware in the network also. It did combining, multicast, and reduction. And I'd recommend reading these papers. And this is their depiction from one of the papers. They had these data routers. They also had the control routers, which use a similar network, but different kinds of traffic. Okay. Is there anything I want to say over here? Yeah, I think one thing they emphasize is scalability of this also, right? You can see that as more processing nodes are added, the number of levels of the tree increases, allowing the total bandwidth across the network to increase proportional to the number of processors. I think this is important, basically. So buses don't have this property, for example, but trees and fat trees have this property. Okay, as I mentioned, we would get to hypercube also. Again, these are all things that were proposed for processor and memory connections. Yes?
In the previous slide, what do they mean by thinned fat tree? Is the name of the...
Where's the thin fat tree?
The very bottom of the previous slide. Yeah, right there. The very bottom.
That's a good question. I don't know what they mean by thin fat tree. Yeah, maybe they don't really show the fatness of the connections over here.
Oh,
I don't know.
So it's just about the schematic.
I believe so. Yeah, I believe so. I'm not sure though. Oh, maybe that's what. Yeah, but not necessarily true, right? I think the fat tree, I would say, is really about the bandwidth. But yeah, maybe that's what they do. I don't know. Yeah. Yeah, exactly. Maybe you're creating a new definition for a thin fat tree, which we don't quite understand. I would recommend reading the paper. Yeah. For my purposes, it's just a fat tree, basically. But of course, every paper has some terminology that they introduce, right? Not necessarily good or bad, but they have to use that terminology that they introduce. Yeah. Okay. So hypercube, this was actually developed for cosmic cube, as I mentioned earlier. This is essentially an n-dimensional cube, or shortly n cube. And you can see different dimensional cubes over here. This is the cube that we're used to. This is the 3-dimensional cube, but this is the 4-dimensional version of it. I believe this is 5-dimensional. We'll see 6-dimensional later. But the good news again here is latency is nice. Number of links is, I guess, kind of nice, n log n. So this has different properties again, right? You have to analyze it based on your traffic patterns. Low latency. The huge downside is it's very hard to lay out in 2-dimension or 3 dimensions, right? But this was proposed for the Caltech Cosmic Cube. This is one of the earliest message passing machines. And they wanted to do this so that they can minimize the communication latency and equalize as much as possible across different nodes. So this is the 3-dimensional hypercube. This is the 6-dimensional version of it. Let's see. Basically, this is a 2-dimensional projection, as you can see over here. You can read over here. But there's not much else. You should really read the paper for more detail. And basically, they suggest that this is a better configuration for message passing because it allows you to communicate nicely between any 2 given pair of nodes. And that was the goal. And this is a beautiful paper, so I would recommend reading it if you're interested. Okay. So before we go into routing, probably we should take a 10-minute break. Does that sound good? Okay, let's take a break until 2 past, and then we'll cover routing and whatever comes next. Any questions before we take a break? Burning? Okay.
Hypercube is basically just like a really nicely laid out and somewhat thinned out version of point-to-point, right?
Which one?
A hypercube.
Yeah, you can think of it that way. Yes, yes. But it's not point-to-point, right?
As you increase and the dimension, eventually it will approach point-to-point.
I would argue yes, yes. And you can see the complexity of routing already in this picture, right? With n equals 6. Yeah. Okay. All right, let's take the break now. Okay, I think we can get started now. Is this working? You think so? Okay, it doesn't sound very loud, so. Okay, remember, we were just done with topology, but I will mention that the motivation for this hypercube was, again, to provide as close to possible point-to-point connectivity between different processors such that they can do message passing and synchronization with each other or communication with each other much faster than multi-stage logarithmic networks, for example, that were common in the past. So as a result, that sort of communication comes at a cost, of course, right, as we have analyzed. So these hypercubes are quite interesting, but their practicality is very much in question, especially for large-scale systems, right? Maybe 64 nodes, okay, you can push it, but 64,000 nodes, yeah, I don't know. Any topology gets strained, actually, with when you go to 64,000 nodes, right? So irregular topologies become very appealing, but irregular topologies are also not great to manage, right? Then you become a multi-computer network, right? And you're not even loosely coupled. Yeah, basically, internet is kind of like that, right? Okay, so let's talk about routing. So routing mechanism, I will talk about mechanism first, and then we'll talk about some algorithms too. And this is, again, another area where there are a lot of interesting ideas. But routing mechanism can be arithmetic-based, source-based, and table lookup-based. So you can do simple arithmetic to determine the route and regular topologies, basically. So if you're at node 0, 0 at mesh, and if you want to go to node 5, 5, row and column, row 5, column 5, you can basically, at any given router, you can do the arithmetic that could get you closer to your destination, right? Clearly. For example, you can, if you're at node 0, 0 and you need to go to row 5 and column 5, you basically go to column 5 first and then go to row 5 next. This is called, I think, YX routing. You go in the Y dimension first and then go in the X dimension. You could do the other way around. You could go to column row 5 first and then column 5 next. Sorry, the first one was XY routing. You go into X dimension first and then go to the Y dimension. The second one is YX routing. You go in the Y dimension first and the X dimension next. And these are very simple routing mechanisms, clearly. At any given router, the router can quickly and independently decide, based on your destination, where you should go, right? Because the topology is very regular and the router has full information about the topology. This is called dimension order routing. Basically, the idea that I gave you is dimension order routing. You traverse the X dimension first and then Y dimension next, or you traverse the Y dimension first and X dimension next, or you pick one of those depending on the congestion in the network, right? But basically, the key idea is based on simple arithmetic, the router can determine where to send a packet. And there are two other methods, source-based and table lookup-based. Source-based is source. Whenever you're sending, you specify the output port for each switch in the route. So you have full information about the network. And the source can say, oh, I'm sending this message to node 6, 6 or 6, 7, row 6, column 7. And I want this to follow this particular route. And here's the route. And you embed that route to the header. And now the router is very simple. The router looks up the header and says, oh, I'm supposed to send this packet to this location. And that's what I do, right? Basically, for each route, the port is specified. Yeah, I think I already said this. No control state is needed for the router. Switches are very simple. You just look up and based on that, you decide what to say. But of course, there needs to be still buffering potentially, right? For source-based. Because what if two sources specify the same output for a given packet? Then the router still needs to do some buffering. There may be conflicts, basically. And there's a large header, clearly, in this particular case, because you embed the route when you start the packet, when you inject the packet into the packet. So this could be pretty large. So this is usually not used because of that reason. But it could potentially be used again. And also, this is not good potentially for dynamic arbitration, right? Because you already specified the route. And you may not have full information about the congestion patterns that are happening in different parts of the network. Table lookup based, here, the router indexes into a table for output ports. So you have a destination that you want to go to, and the router basically determines the destination output port based on some table lookup. And again, this could be a small header. Basically, every router makes a decision, but switches will be more complex this way. So hopefully this is easy, right? You determine your route based on some methods. And again, table lookup base can support many different kinds of methods, right? It doesn't have to be arithmetic. But arithmetic is simple. You don't need to do any table lookup in that particular case, right? Of course, you can implement the arithmetic routing using table lookup as well, but table lookup is much more general, right? It could be for any arbitrary topology. You could do table lookup, right? Okay, so that's the mechanism. There's also the algorithm, which is different. And there are three types of algorithms for routing in general. One is deterministic. Deterministic algorithms always choose the same path for a communicating source and destination pair. Basically, you're communicating between node 0, 0 and node 5, 5. You always go through the same path. You don't exploit the path diversity for a given communicating source destination pair. Why could this be good? We'll see. Oblivious, you can go through different paths basically, but you don't consider the network state. So going from, again, node 0, 0 to node 5, 5, you can choose different paths, but it's oblivious to the state of the network. That's why it's called oblivious. Okay, let me maybe quickly do this. It's going to be very easy, but let's do it, I guess. Yeah, the difficult part is, okay, stop sharing. And then what do I do again? Share advanced content from second camera. If we can get to it. Okay. Wow, there's a lot of white space. This is like a badly formatted paper. You have a lot of white space and no text. Yeah. So basically, I think this is simple, but let's say you have a mesh. I don't have the links here, but I guess now I have the links also. Mesh is easy to draw also, as you can see. It's hard to make a mistake. Okay, I'll draw one more. It doesn't hurt. And you want to go from here to here. Deterministic XY routing, which we will see XY routing, but deterministic means you always pick the same route. It could be this always, right? In some way. And that's the only route you pick. If you're going from node 0 to, I don't know, is this node 11? I think so. Yeah. But basically, if you do that, you're not exploiting path diversity at that point, right? If you are, let's see. So normally what's used is XY routing, as I said, right? This is, you basically traverse the X dimension first to go here, and then you traverse the Y dimension. That's XY routing. This is an example of dimension ordered routing. You basically order the dimensions and route along one dimension first and the other dimension next. It could be applicable to 3D structures as well, clearly, right? So that's one example of a deterministic routing. You always, communicating between 0 and 11, you always go through this route. And you can see, you can already see the downside of dimension order routing, right? If you're communicating between, I don't know, 1 to, what is it, 7, you also go through this route. If you're communicating between, I don't know, 2 to 3, again, you go through this route. So basically, based on your contention patterns, all of these communications are happening on the same links. Even though you have a lot of path diversity in the network, your routing algorithm is unable to exploit that path diversity because you basically say, oh, I want to do just XY route, right? As a result, you get a lot of contended links along the places where these communications actually overlap with each other, right? But this is an example of deterministic routing algorithm. It's very simple as a result of its determinism. Oblivious means that, okay, I'll use the same picture. Why not? We just needed more colors, but we don't have colors. But oblivious means that, okay, you want to go from here to, I don't know, let's pick another one right now. Here, you can basically pick different paths. You can go from this way. I don't know, you can go this way. And you can probably find out some other paths, right? You can do XY, you can do YX. Okay, you can do YX, XY. Those are two simple routing mechanisms that routing algorithms that can actually get you to both places, and you can choose either one depending on some randomness, right? You can say, I'm going to flip a coin. I'm going to go through this way. Basically, I'm going to flip a coin. I want the XY 50% of the time, meaning I do this one. And 50% of the time, I'm going to do YX. That's an example of an oblivious algorithm, right? Now, this exploits path diversity, right? The previous one, deterministic, didn't exploit path diversity. This exploits path diversity. But it exploits path diversity in a manner that's not aware of the congestion in the network. It's not network aware. Now you can make this network aware. That makes us, that basically leads us to the adaptive algorithms. And basically you choose XY if you think the contention downstream is lower on this path. You choose YX if you think the contention is lower when you take this path. This requires some network state awareness. It requires some information about the network. And this information can be obtained locally. You basically look at this link, how congested it is over time or right now. You basically look at this link and how congested it is. You can basically look at your local information as a router and make that decision. Or you can make a more global. You can look at a more global information, which requires collecting some statistics about the global patterns over here, global communication patterns potentially, or global congestion patterns. And based on that information, you choose either XY or YX. That's the adaptive algorithm, basically. So those are the three different types of routing algorithms: deterministic, oblivious, and adaptive. Right. Now we can go back to our picture. We don't need to switch camera. Okay. Basically, adaptive can choose different paths, adapting to the state of the network. That's the only difference between oblivious and adaptive, adapting to the state of the network. So how to adapt can be based on local or global feedback, as we discussed. Now you run into also minimal or non-minimal paths. Basically, okay, I guess it's not going to be visible for people on the internet, but maybe it's okay. So minimal path is the minimum number of hops that you need to traverse to actually get to a destination. You can have non-minimal paths in this particular case, right? Basically, you can go from here to here, go back, and then basically you do some zigzags, go back along the way, and then eventually reach your destination. That's called non-minimal, right? So non-minimal gives you more flexibility, but it increases your latency, clearly. So whether you're adaptive minimally or non-minimally is also interesting. Right? Okay, deterministic, I'm going to go through this quickly because we've explained this with a picture also. Basically, all packets between the same source and destination pair take the same path in this particular case. It's called, dimension order routing is one example of deterministic routing. First traverse the X dimension and then traverse to the Y dimension. For example, XY routing was used in early supercomputers like Cray T3D. And many on-chip networks actually use it as an example because it's simple, right? It doesn't complicate the router that much. And it gives you deadlock freedom. We're going to talk about that by design, let's say. There are no cycles in resource allocation. Basically, different routers cannot make decisions that lead to some resource deadlock because some resources not free anymore. You cannot route because your routing always goes the same way. So there are no turns that would lead to deadlock, basically, in your routing. Of course, the downside is this could lead to high contention, as I showed you, and it clearly doesn't exploit path diversity because there are many ways to get from, well, depending on your topology, there could be many ways to get from point X to point A to point B, right? Okay, so deadlock, let's talk about this basically. Deadlock basically means there's no forward progress, right? It's caused by circular dependencies on resources, especially on a network. And for example, each packet waits for a buffer occupied by another packet downstream. So in this particular example, let's see what's happening. Packet 3 is waiting for a buffer that's occupied by packet 4 because packet 3 needs to go this way. Packet 4 is already occupying that buffer. Packet 4 is waiting for a buffer that's already occupied by packet 1. Packet 1 is waiting for a buffer that's occupied by packet 2. Packet 2 is waiting for a buffer occupied by packet 3. And this is your circular waiting, let's say. And that's why you have a deadlock in this particular case. Either you don't have enough buffers, potentially. This could be solved by adding more buffers. I said you never run into this situation. Good luck with that. Then you're limiting the number of requests. It could be solved by fixing your routing algorithm so that you don't run into this situation, which we will talk about. It could be solved by detecting the situation and breaking it, right? Potentially, you could detect that this is happening, there's a circular dependency or graph of resource allocation. It requires a lot of effort to detect it, of course, and then you can break it somehow and say, I'm going to throw this packet away and tell the sender to resend that packet. Right? Okay, so basically, I've already said this, I think. You want to avoid, you can avoid cycles in routing by making your routing algorithm and ensuring that your routing algorithm doesn't result in such a situation, basically. I think that's a clever way of handling deadlocks. So dimension order routing, for example, is an example routing algorithm where you cannot build such a circular dependency. So by design, the circular dependency is not possible. For the proof of that, I will recommend you to read a paper. Basically, the key idea is to restrict the turns each packet can take in the network. And if each packet can go, if each packet can go XY, 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 you will not run into this problem, basically, because some of the packets need to be going YX over here. Okay, we'll talk about this a little bit more. As I said, you can avoid deadlock by adding more buffering or escape paths, right? Meaning some other path you can escape to. Again, this is not a very scalable solution, but this could save you if your resources are not extremely over-provisioned. Or you could detect and break deadlock, as we discussed, right? This requires some kicking out some of the packets that are already occupying some buffers. Okay, this is a turn model to avoid deadlock, basically, that showed that you can actually design your routing algorithm to avoid deadlock. And your routing algorithm can still be adaptive, basically. And the idea is analyze directions in which packets can turn in the network. And you can see that there are different turns. You can see the possible turns and simple cycles in a two-dimensional mesh. That's how the packets can turn. And you can determine the cycles that such turns can form. And you can prohibit just enough turns to break possible cycles, resource allocation cycles. So you can see, for example, in this figure, the 4 turns allowed by the XY routing algorithm. And we've discussed this kind of earlier. And then they talk about some ways of actually 6 turns that complete the cycles and allow deadlock. So if you have these 6 turns, then you lead to deadlock. And I'd recommend reading this paper. This is a seminal paper on the topic of, it builds basically a turn model to enable deadlock freedom in routing algorithms. And it has a lot of influence in the field. Okay, any questions? Okay, let me give you an example of oblivious routing. There are many algorithms, but probably the most famous of this is Valiant's algorithm. Valiant is also credited for developing the bulk synchronous processing model, where each thread does exactly the same thing, and then they synchronize, and then they keep doing this exactly the same thing. This is a bulk synchronous model. You have a program or single program multiple data model. But he was very interested in basically parallel programs and how to actually make them execute well on like network processors, network multiprocessors. And the goal here is to balance the network load. And the idea in Valiant's algorithm is, again, oblivious means that it's not aware of the network state, right? So you usually resort to randomization. You randomly choose one path when you send a packet from a source to a destination. At the first time, every time you randomly choose a different path. That's one way of doing it. Valiant's algorithm actually divides the network into quadrants. Okay, I don't want to go back to that, I think. But basically, imagine, maybe I will go back to that. Why not? So much overhead to switch between these threads. No, stop sharing. There should be a very simple function that enables me to do that, but I guess not. Okay. I don't know if this is visible. What do you mean? Oh, okay, yeah, you're right. For some reason, it was partly visible. Okay. So maybe we will use another picture over here. So basically, you have a huge mesh. Imagine this is a mesh. You divide into quadrants. And basically, you are some node over here. And you want to communicate with some other node over here, let's say. What you do is, first, you randomly choose a quadrant and a random node in that quadrant to route to. So basically, you do an intermediate route. So you go from here, randomly, you pick a node over here, and you route, let's say, YX over here. Maybe we should do XY, I don't know, but in some way, basically. And then YX over here. So basically, there's a random node that you route to first, and then from that random node, you go to destination. And I mean, another thing could be like communicating from here to, I don't know, here. You first route to some node here, and then go from here to here, right? So that's the idea, basically. Of course, this is, you may not do it exactly this way, right? You may want to do it more cleverly. If the nodes are too close to each other, maybe you don't want to do it. But if you have a very large network, this may be a good idea to do it. So let's talk about what this achieves. I don't want to switch camera. I don't want to share back. So what this, yeah, basically the routing that you use can be different, right? Between source and intermediate and destination, you can use dimension order routing. Or you can use different routing algorithms. So what does this achieve really well is it randomizes and balances network load, right? So basically it maximizes your path diversity in a sense. That may not always be a good thing, right? But clearly this is very good at balancing network load across a network. Downside is non-minimal packet latency can increase. And as I showed you, it does increase, right? In particular cases, because you're not taking the optimal path. You're going through some intermediate node, which may be somewhere, which may be increasing your distance to the destination that you really want to go to. But of course, people have developed optimizations for this. So the problem with deterministic routing is it's really bad for path diversity. You run into these very bad cases where you have contention. This is really great for balancing network load, but balancing network load is very bad for latency. So why not do this when you really need to do it? For example, you can do this on high load when your network is very loaded. Okay, switch from deterministic routing to randomized routing like this. Or when you think part of your network is loaded and you're sending stuff to that part, start doing something like this. So you can basically be more intelligent in how you employ this general idea, right? You can restrict the intermediate node to be closed, for example. You don't do it like randomly across the quadrants like I showed you. You can basically be more distance aware while you're doing it. Maybe not congestion aware. You can also be congestion aware as we discussed. So basically that becomes less oblivious at that point, right? Now you become actually more congestion aware, which becomes more adaptive. So basically variance algorithm can be actually employed in an adaptive fashion as well as an oblivious fashion, as you can see. Okay, and if you're interested, I'd recommend reading these papers. And this is the paper that introduced bulk synchronous parallel processing as well. Okay, so let's talk about adaptive. Adaptive is basically, I kind of gave you an example of adaptive. Adapt variance algorithm. Instead of randomly choosing a node, decide based on the congestion. But you can use any other algorithm also. Router, the key idea in adaptive routing is router uses network state to pick a port to decide. Now there are two versions of it, minimal adaptive and non-minimal or fully adaptive. Minimal adaptive means you always choose a productive port. What is a productive port? Productive port is the port that reduces your distance to your destination. Basically, you make progress to your destination, whereas a non-productive port increases your distance to the destination. Does that make sense? They can always go back, basically, right? So minimal is you always choose a productive output port. Of course, there's a trade-off, right? The output port may not be available, then you're choosing to wait in the buffer. But if you are non-minimal or fully adaptive, you can say, oh, I'm going to choose a non-productive part. This is also called misrouting. Basically, you misroute the packet for some time, and hopefully it will reach a path that's less congested, and it will get to its destination. Hopefully faster than it would have if it were waiting in the router. That's the idea. Because it's always a trade-off. If you insist on choosing a productive port, you're going to wait. If you say, okay, I'm more flexible, I can go back a little bit. Hopefully I'll get to my destination faster. Then the trade-off is you're going to traverse more links, but hopefully the time you spent is not going to be as long as the time you spent waiting in the buffer. That's the idea. Of course, this trade-off may not always work well, right? Because the network may be so congested that you keep going around from router to router and router to router until you get to your destination. Now, the downside, of course, with non-minimal adaptive is you have a live lock problem, right? How do you ensure that you actually ever reach your destination if you're misrouting once in a while? So you may be actually going from router to router, but you may never get to your destination. How do you guarantee you get to your destination becomes a problem with this sort of algorithm? Whereas that That doesn't happen with minimal adaptive, right? You don't have this live lock problem. When your buffer actually, when it's your turn in the buffer, you basically proceed. Okay, so minimal adaptive is aware of local congestion. This could be made aware of global congestion also potentially. But minimality restricts achievable link utilization. Now load balance basically. With non-minimal adaptive, you can achieve better link network utilization and load balance, and also better latency in the when there's congestion. But now you need to guarantee live lock freedom, and we're going to talk about that tomorrow, hopefully, when we talk about deflection routing. So this is also called a deflection, basically. Whenever you're misrouting packets, at least one way of implementing it is deflecting the packet to some other node that it doesn't want to go to, right? Some other node that's non-productive, basically. Okay, so adaptive routing is actually very useful because it's useful for other purposes than just performance, load balance, etc. You can avoid faulty links and routers, and you can route around faults. And deterministic routing clearly cannot handle faulty components. If you design your router to be strict, it does this arithmetic equation and it decides the output port. What if that some link is not available over there because there's a fault, right? Too bad. You have to change your router right now. But if your router is hard-coded in hardware, you cannot change it. So your chip is dead at that point. So the downside of adaptive routing, of course, is, well, when you actually want to be fault tolerant, you need to change the routing table to disable faulty nodes. So if you have a routing table, like a table lookup-based router, which is more complicated, then you can basically change the routing table based on the faulty links, faulty nodes, etc., that you detect in your network, right? Every routing table can get updated based on the fault information. This assumes, of course, you detect the faulty link and router. So hopefully this is obvious, right? And there are a lot of issues actually related to this, and I would recommend looking at papers if you're interested in it. We're not going to cover a lot of issues, because how do you guarantee delivery? How do you design algorithms that can guarantee delivery and at the same time low overhead? And this is one of the papers that we had done in the area a while ago, if you're interested. Okay. Any questions? That brings us to buffering and flow control. Okay, let's talk about buffering and flow control. I mean, we've talked about buffering and flow control a little bit when we talked about circuit and packet switching. I'm not going to revisit circuit and packet switching right now. Maybe I will briefly mention that packet switch networks also usually behave this way, because we're going to talk about some issues in routing and buffering. Basically, you have a message, right? The message has a header, payload, and error code. And this could be a packet also, a message. I'm going to use packet and message exactly the same. Header contains the routing and control flow information. So it's using the headers that you really arbitrate inside the routers, right? And then payload basically can get sent. It carries data. It can be further divided into smaller pieces. And then there's usually an error code to make sure what you receive is what matches the error code, right? So in the end, you do a check at the end, checksum or CRC or some sort of error code checking. So usually this is a packet that's used in a network. But let's talk about, we're going to get back to this later on when we talk about how to handle buffers in wormhole routing, for example. But let's talk about how to handle contention. Basically, one of the things that a router has to do fundamentally is handling contention. Two packets, in this case these white ones, are trying to use the same output port, same link at the same time. What do you do from a router? You're the router, what do you do? From the router's perspective, you have multiple choices. I think we've covered all of them, so I'm going to go through that. Buffer one. This requires you to have buffers. You can drop one. This is something that we do not cover actually. And basically say, okay, please resend. This is a dropping network. Or you could misroute one, which we just covered, or deflect one. Meaning, okay, these two packets are going to want to go to this link, but I'm going to send one of them to that link because I only can send one. I'm going to send the other one to this link. Even though that's the link it doesn't want to go to, right? It's going to increase its distance to the destination. Why? Well, because this link is available. And hopefully it will get to its destination faster that way. I'm congested. I clearly cannot send two at the same time, but I'm going to use this link so that that packet goes from me. It's also called the hot potato routing. You can think of these packets as hot potatoes, right? You cannot keep any potatoes because Hot, these are hot, right? So you basically send the hot potatoes to wherever they can go. Hopefully, at least one should go to the port that it wants. Right? That's the idea. So in other words, you're using links as buffers, right? The network links are being used as buffers. And assuming you have, you don't have a lot of contention, that buffering may be enough for your communication across the network, right? This is a cool idea, actually. It was developed in 1962 by Paul Baran. There's a seminal paper on distributed communication networks. And it was considered for the internet also. People actually said, oh, why don't we actually use this hot potato routing for internet? But usually it has some trouble in high contention scenarios, as we will discuss. So these are the three fundamental things a router can do, basically. Can you come up with another one? Of course, you can combine these, right? You can have some buffering, deflection, sometimes you drop. The hybrids are possible. And hybrid always comes with additional complexity than either any of these mechanisms alone. Okay, so clearly there are trade-offs, and we will cover some of these trade-offs. And I've already given you some of the trade-offs, right? Buffering is, well, it requires buffering now, and buffers add complexity. Dropping requires back signaling. Well, buffering also requires back signaling, as we will discuss because of the allocation of the buffers, but dropping requires back signaling to the sender. And the sender needs to be informed right now. Normally, you don't inform the sender. It's a local decision that you make. Misrouting now requires, how do you handle live lock, right? But it doesn't have the downsides of buffering and dropping. That's the nice part, basically. You don't have this back network that you need when you misroute. If the only thing that you're doing is misrouting, there's no need for this back network or back messaging that needs to go through some other router or the source. Okay, so clearly it's a trade-off, and we will discuss that. So let's talk about these flow control methods. Certainly, circuit switching is one flow control method. Also, if you think about it, it's a flow control method. Once you set up the circuit, there's no flow to control. You just need to make sure that nothing else conflicts with that flow. Right? We will see some examples like bufferless, store forward, virtual cut through, and wormhole. Now I'm adding more terminology for you. But let's revisit circuit switching. Circuit switching is a flow control method where your resource allocation granularity is large. Basically, you pre-allocate resource across multiple switches for a given flow. Flow is basically communication between a source to destination, a given source to a given destination. So to be able to do this, as we discussed, you need to send a probe to set up the path for pre-allocation, either on this network or some other network. But the big advantage is there's no need for buffering, no contention, because you've dedicated. It's isolation. Basically, you provide isolation for that flow, right? And you can handle arbitrary message sizes. That's nice, actually. And because you don't need to buffer them, that's also great, right? You basically keep pumping data on this link. Of course, as we discussed, there's lower link utilization because two flows cannot use the same link. And there's handshake overhead to set up this circuit. Right? Okay, hopefully that's clear. Let's talk about bufferless deflection routing. We already talked about this also, but in the extreme case, you never buffer packets in the network. When two packets contend for the same link, one is deflected. And this is the paper that I mentioned on distributed communication networks. This is part of your reading. And you can do the reading, actually. I would recommend it. Okay, the basic idea is very simple. This is the destination that both packets want to go to for some reason. And the router basically decides red packet goes here, and the blue packet takes the scenic route. It sees this edge routers before it goes to the destination, right? That's the idea, basically. So it takes longer. Clearly, it takes longer for this blue packet to get to the destination, but you don't have buffers. And maybe it could have taken shorter, actually, if there was more contention on this router. And new traffic can be injected whenever there's a free output link, basically. So this each router or each injector, let's say, each processor makes a decision as to when it can inject a new packet. If all of the links, output links, are busy, it cannot inject a new packet, basically. So you can see that this could cause a problem. If lots of packets are circulating around the network and never getting to their destinations, you cannot even inject new packets because you have limited buffering capability. And when I say limited buffering capability, it's really the number of links that we're talking about, because this is the extreme case where you don't have any buffers. Okay, so the upside, of course, is this. You eliminate your input buffers. So this is what a modern router looks like, actually. You can see it's a 5x5 crossbar for a mesh, two-dimensional mesh. And you can see these are the 4 neighbors that you have, and then there's a local injection port and a local ejection port for data. So it's in the end, it's a 5x5 crossbar. You can simplify it by taking advantage of the fact that this is kind of local, but it requires a lot of optimization if you want to simplify it. But basically, if you go bufferless, you eliminate a lot of these input buffers. We're going to look at the input buffers in a little bit. You replace it with some deflection router logic. We're going to look at the trade-offs tomorrow of what this entails. But basically, there are issues in bufferless deflection routing, live lock. Router actually becomes a bit complex if you want to solve the live lock freedom problem. And there are multiple solutions to the live lock freedom problem. One solution is actually having a total order of packets on the network. Now we're going back to the ordering, right? You have a total order of packets in the network, and you basically ensure that the highest priority packet always gets routed to a productive port in each router. And as long as you obey this total order, you never get into a situation of live lock. But of course, it turns out this total order is easy to form potentially, but it complicates the router significantly because router now needs to have another order that it needs to obey in terms of its prioritization. And we will see this. And so basically, the devil becomes goes into the details when you actually want to do something like this. And we tried it. And I think there's a lot of interesting insights. And there's also another issue, right? If you don't have buffers, you're limited to the number of links, and your capacity in the network, the amount of load that you can handle, is limited, clearly. If you have buffers, you keep injecting stuff into the buffers. And the amount of load that you can handle is higher. Whereas if you don't have buffers, you're using the links as buffers. First of all, you cannot keep injecting forever because you have limited number of links. And you may not be utilizing your links extremely well because you don't have buffers, because some packets are circulating, taking scenic routes around the network, right? Okay, so basically, I think there are a lot of interesting issues to solve in deflection routing, and we have looked at it over the course of 6 years, and we will discuss some of it tomorrow. And this is the original paper where we talked about it in the network on chip context, because I think in network on chip context is a lot easier to build this. And there are other properties on network on chips that make it easier, as you will see. Okay, these are some papers. Hopefully we will see that. And there's bufferless hierarchical rings, or mostly bufferless hierarchical rings. And if you're interested, this is a review paper, and this is a more recent paper that we have just put on archive actually last week, I think, that talk about topology routing and flow control issues in deflection-based on-chip networks. And one of the big benefits of this reducing the buffering is really energy and complexity. And that was our argument. Your performance, basically your performance will not be as high as a buffered network, no question about that. But you gain a lot of energy and complexity benefits. Okay, let's talk about some other methods of flow control. So bufferless is nice, but let's talk about buffered now. So then the question becomes how you manage buffers. So store and forward is one early example. It's kind of not great, so I'm going to go through this relatively quickly. Basically, each router stores the entire packet before you can forward any part of the packet to the next node. That sounds stupid, right? Yes, it's not very good, basically. Basically, the flow control unit is the entire packet. Your FLIT is the same as your packet. FLIT is the flow control unit, right? So you have the source and destination. You have this packet. You can start routing it. And as a result, this leads to high packet latency and requires buffering for an entire packet in each node. Basically, this is the idea. You have to wait for the packet to get to the next node before you can transfer it out of the next node. Makes sense, right? Well, it's not very good because you could have chopped the packet and some part of the packet could have been in the next node while some part of the packet could have been in this node, right? And that's the next idea, basically. This is called, basically, can we do better? Yes, cut through flow control. I mean, some of the terminology I really don't like here, as you can see, what does cut through mean? We will see. But basically, it's another form of packet-based flow control. And the idea is very simple. Start forwarding as soon as the header is received and resources are allocated. So basically, you have the source. So it reduces latency, great, but still allocates buffers and channel bandwidth for full packets. Again, I'm going to go through this quickly because I want to reach somewhere else. Okay, let's see the example first. But basically, okay, here you can start forwarding to the next node, right? So the packet can be distributed across nodes in this case. But if packets are large, you're back to square one almost. Yeah, I'll go through this relatively quickly. But what do you do if the output port is blocked? You let the tail continue when the head is blocked. So you basically divide the packet into head middle and tail parts. And you can absorb, basically what happens is the output port is blocked. What happens is the entire packet has to go over here. Entire packet needs to be buffered inside a single node. Because here we're looking at an example where the output port is not blocked, right? Because somebody else is not using it. But if this output port was blocked, the entire packet comes over here. And now you need storage for the entire packet in this particular case. Okay, so basically you require a buffer large enough to hold the largest packets, which this cut-through flow control, and I admit that I didn't give you all the details related to it, it degenerates the store and forward with high contention. So people have tried to solve this problem, and this is the state of the art. It's called wormhole. Basically, you have a worm, and you chop the worm into pieces, and different pieces of the worm can be at different locations, and the allocation granularity of is based on the chopped pieces. So packets are broken into smaller flits. Now we have this flow control unit. And that's the buffer and bandwidth allocation unit. Before it was the packet. Now we're chopping the packet into smaller allocation units. And you can see that the head is here, body is here, another body flit is here, and the tail flit is over here. Okay. So flits are sent across the fabric in a wormhole fashion. So basically you have the head of the worm, body follows the head, and the tail follows the body. And the worm leaves traces in the router as it goes through, meaning, oh, I'm the worm for this packet, and whatever comes after me should follow the same route. That's the idea. And it's pipelined this way. If head is blocked, the rest of the packet actually stops. So you don't need allocation granularity required for the size of the packet. Basically, the worm stops moving if the head is blocked. And the routing information is only in the head, basically, except there is some additional control that you leave. For example, this router makes a decision for the head. The head needs to go up, for example, for whatever reason. It basically leaves a little note for the body packet so that the body packets get routed in the same direction. So technically, you don't need to make the same routing decision again and again and again for each flit. You make the routing decision on a packet basis, which is the head, in other words, for the head flit. Okay, this is what I discussed. How does the body or tail know where to go? You leave some information when you make the routing decision. And you need to associate the IDs of messages, of course. So you need to make sure it works right. And the nice thing is latency is almost independent of distance for long messages. If your message is long, your worm gets distributed across the network and your latency is not bad. Okay, let's talk about the advantages. So this is lower latency than store and forward flow control, and it leads to more efficient buffer utilization as well because you don't need huge buffers. But this has limitations. It suffers from head of line blocking, which is really where I wanted to get to. If head flit cannot move due to contention, another worm cannot proceed, even though links may be idle. And this is not good because it basically reduces the link utilization of an otherwise good network with good path diversity. So basically, this is a problem with the way you're doing routing. Arbitration. So let's take a look at this. So let's assume that these are your input queues, two of them. There's some switching fabric, which is a crossbar, and then these are your outputs. And these are what different packets or flits, whatever you want to call them, want to go to. So this flit wants to go to output port 1. This flit also wants to go to output port 1. This flit wants to go to output port 2. This flit wants to go to output port 2, and you get the idea basically. And they're in two different input queues, which doesn't matter. So there needs to be some arbiter that decides where each flit goes. And in this case, both of the flits at the head of the queues want to go to output port 1. Right? And you have a problem. Why? You can only pick one. Now, once you pick one, what happens here? Well, it becomes idle. And this is called head of line blocking if you actually do the arbitration only at the head of the queues, right? So you have two queues and the head flits, or the flits at the head of the queues, both want to go to the same output. Some other flits in some other part of the queue will not get allocated to an otherwise idle port. So how do you solve this problem? You make the arbitration more complex. Consider all flits in all input queues, right? That's one solution to the problem. You can kind of do out of order scheduling from a queue, basically. That's possible. It complicates the router again, right? Does that make sense? Yes.
What would happen if you have couldn't the potential stall of a head cause an entire part of the mesh to not be used?
Yeah, exactly.
Because like if it's exactly in the middle and it's like line wise, it would be potentially the body and tail would be blocking other heads.
Exactly. So this head of line blocking is not just one in one router, but it has implication for the other routers also. Yeah, that's why it's not good. You could do out of order scheduling clearly with the heads, but that complicates the router. So clearly solving this problem is possible with out of order scheduling. You don't look at just the heads in the heads of the queues, but you look at all head flits that you have and arbitrate among them. But that complicates. Yes.
So if I understand correctly, everything with 1 belongs to worm 1, and everything with 2 belongs to worm 2, right?
Not necessarily. These are really just output ports, basically. So basically, these are. I actually said I think head flits only, but basically these are the head flits that want to go to output port 1. Let me give you another example. Maybe it'll become more clear. I'll give you a pictorial example soon. But basically, a worm can be before another in the router input buffer, and due to the FIFO nature, first in, first out nature of the input buffers, that's the real problem. The second worm cannot be scheduled, even though it may need access. It may actually need to access another output port. That's completely independent, which is the picture I showed you. So let's take a look at this example. So assume that this link is blocked by other packets, and these blue packets want to go to the blue router. These red packets want to go to the red router. Now the blue worm is coming. Blue worm is going in the right direction, XY routing. Now this buffer becomes full. Blue cannot proceed anymore, right? This is the situation that I think you mentioned. You'll empathize with it. Now the red one, even though this channel is completely idle, red packet is blocked behind the blue, right? Okay, I mean, this is what happens, unfortunately. Okay, and red holds this channel remains idle until the read proceeds. This is because you have a single queue, right? And you look at that single queue. So the idea that's developed to solve it, I mean, one idea is out of order scheduling, of course, right? But that's more complicated. The virtual channel flow control was developed to solve this. And the idea is to multiplex multiple channels over one physical channel. Or in other words, divide up the input buffer into multiple buffers sharing a single physical channel. So these are single queues, as you can see over here, input queues. Basically, you divide it up into multiple queues over here. And you can divide up based on the output ports also, right? You can partition these queues such that these are the ones that go to output port 0, these are the ones that go to output port 1, such that you don't have dependence between different output ports. And the reason before the dependence was because we could only schedule from the head of the queue. Now we can schedule from the head of 2 queues. So hopefully, the ones that require output port 0 are here, the one that require output port 1 is here, and they don't do head of line blocking to each other. Does that make sense? So that's one way of designing a virtual channel router. And this is the basically simple idea. And assuming that you want to keep the buffer size constant in a particular input port, you have, instead of having 16 flit, a FIFO buffer, you basically divide into 4 virtual channels, right? And you can, of course, arbitration still becomes a little bit more complex because you need to look at, instead of looking at 1 head flit over here, you look at 4 head flits over here, right? Clearly, it's more complex, but this is hopefully less complex than looking at doing out of order scheduling out of the 16 entry buffer. Now, you may say, okay, in our processors, we do complicated out of order scheduling, and that's true. Why not do it in our routers? That's a good question. I don't know. I think that's basically complexity again, right? If we keep doing out of order scheduling in all of the components and our power requirements will go up significantly. Okay, so let's take a look at virtual channel flow control. Let's say we have 2 virtual channels right now, exactly the same example. This is still blocked. This input, this link is still blocked by other packets for whatever reason. And the blue ones want to go to blue, the red ones want to go to the red destination. Now blue ones occupy 1 virtual channel, and that virtual channel gets blocked because the buffer is full again, blue cannot proceed. But now the red ones can go through the other virtual channel to their destination. And that's the idea basically. Without resorting to full out of order scheduling with multiple queues, you can solve a lot of the head of line blocking problems. Okay, and a modern router actually looks like this also, basically. I won't go through this in detail. Hopefully we'll cover this more tomorrow. But you have a bunch of input channels. and you have these buffers, and buffers are divided into multiple virtual channels, as you can see. And the virtual channel identifier, you basically allocate virtual channels over here, hopefully related to the output channels, so that you minimize head of line blocking. And then there's the crossbar. So there's some arbitration logic. There's some routing logic. There's virtual channel allocation logic. And there's a switch allocation logic once you do the routing, because who gets to be routed from one input port to output port? That's the switch allocation, basically. And because you have a lot of buffers, you need to ensure that the downstream router has buffers, right? And how do you know whether the downstream router has buffers you can send to? That's what this credit is. That's how you do the flow control. Basically, you get some credits, and that tell you whether the downstream router has buffers. And you also send credits out, saying that, oh, on this input channel, I have some credits, so I have some buffer availability, basically. Communicating buffer availability is necessary also if you have buffers. And this is one way of doing flow control, because you don't want somebody sending you a packet or flit if you don't have anywhere to buffer, unless your protocol is designed to handle that packet that is sent to you speculatively, right? Okay. So there are other uses of virtual channels. Virtual channels are nice, actually, because they can be used to avoid deadlock and prioritize traffic classes. Some quality of service can be handled in the virtual channels. So one thing you could do to avoid deadlock is you basically switch to a different channel, virtual channel, so that you can break the deadlock, right? Okay, basically some turns, based on a turn basis, turn by turn basis, you can use different virtual channels, right? That way you're essentially dividing the network to two different types of traffic that are turning in different ways, right? If multiple different types of turns are not compatible with each other, if they're used in the same network, if they're divided into different virtual channels, maybe they're okay, right? So you can have different turn models for different virtual channels. As long as you can isolate them from each other, you can avoid deadlock. You can enforce some order of virtual channels. You can use escape virtual channels, have at least one virtual channel that uses deadlock-free routing. Everything else may use deadlock not free routing, let's say. And ensure each fleet has fair access to that virtual channel. That's one other way of avoiding deadlock with virtual channels. And there's also a protocol level deadlock. You can ensure that address and data packets use different virtual channels. And this prevents cycles due to intermixing of different packet classes. We may talk tomorrow, again, protocol level deadlock. I may give you an example. But because reply packets may hog the request packets, as a result, you may have a deadlock at your protocol level. You may never receive a reply, for example, or you may never receive a request, depending on what kind of request it is. As a result, by mixing the request and replies, you may actually lead to deadlock problems. And if you have different virtual channels that are used for different types of traffic, requests and replies, you can actually avoid this problem also. And then there's prioritization of traffic classes. Some virtual channels can have higher priority than others. You can designate the virtual channels to have different kinds of bandwidth, for example, guarantees, if you will. So now you get into quality of service. So it's always good to have more queues to enable different quality of service classes. Okay, so let me review. This is a store and forward. It's not very smart. You shrink the buffers and reduce latency. You get cut through wormhole. Well, I would say wormhole. But wormhole has the head of line blocking problem, which we also showed. And I think we already discussed this. And virtual channels actually solve this problem. But now we're complicating the router, basically. At every step, we're complicating the router. Yes?
Can't we still get head of line blocking using virtual channels? Because each to essentially any virtual channel, right?
You can also restrict that potentially,
Yeah.
right?
Because
Based
then
on the output port.
Because then we can just have 4 flits output that go to the.
Yeah.
We end up with the.
Yeah, that's true. That's true. Yes. I mean, this reduces the head of line blocking problem, but it doesn't. By no means it eliminates. It doesn't eliminate the problem. You're right. If you really want to eliminate the problem, you need to go full out of order scheduling, right? You have to be able to examine each flit and say, oh, this is the flit that can go, and it goes, right?
Couldn't we just do like sort of redirect the flits if they like we can use the whole credit system to notice that if another this thing doesn't work very well, the follow buffer is full. And then we can just redirect the flit.
Another path meaning another link. Yeah, sure. But that makes your complexity, arbitration complexity more. Sure.
But then at least we won't have the.
Yeah,
hard
basically
line
you're
at the
saying
end.
we deflect the flits, right? Yeah. I think deflection actually helps a lot of these situations where you're blocked. I like the idea of deflection, sure. But that does complicate the complexity of the router. Now you have to do buffered flow control and also routing and arbitration. And on top of this, you need to add deflections in case you cannot get what you want, right?
I guess then we don't have to add the virtual channels.
Yeah.
So
Yeah, sure. If you're completely based on deflection, you don't need any of this complexity. I agree, and we will see that tomorrow. That's very appealing, I think. This buffering, all of this buffering and virtual channels, you don't need this complexity if you manage your flow control in a different way. If you go bufferless, let's say, and use deflections. Yes.
What's the advantage of wormhole over circuit switching? Because I thought like a big advantage of switching to the whole packet switching method is that if one output channel is blocked, you go through the other one.
What's the advantage of wormhole over circuit switching? So we're talking about all packet switching in this case, right? These are all packet switch networks.
Should they be looked in different veins though? I thought that like it doesn't make no sense to compare packet switch versus circuit switched.
Well, packet switch, circuit switch, sure, yes. And we've kind of compared. And certainly circuit switching provides you a much simpler router in the end, right? But it suffers from the inability to dynamically utilize your routers. So I think the same arguments again apply. Wormhole is a way of implementing packet switched networks. And it has the upsides and downsides of packet switching. And circuit switching has some other upsides and downsides. Yes.
But wouldn't wormhole also be useful in circuit switching?
Mm-hmm. It could be, yes.
I think that's a totally other dimension, isn't it?
I see what you mean. Yeah, sure, certainly. I mean, you can apply the idea of wormhole to circuit switching, yes. I mean, in a sense, circuit switching systems already do that, right? If you're dividing a packet into smaller chunks that need to be transferred, circuit switching systems already do that. The reason why wormhole was developed in the packet switching notion was to ensure that, okay, only the head flit arbitrates, everything else just follows. But yes, I think the same notion already exists in the circuit switching, except head flit never arbitrates in circuit switching. You set up the path in some way, right? Exactly, yeah. There's basically instead of head flit arbitrating, you set up the path once. Yeah. That makes sense?
Yeah, I guess so. It just seems to me very much that like it seems to me like that wormhole is just a flow of information, right? Like that follows this worm, sort of like the circuit switching. Yeah.
But circuit switching again, you're not following a head flit. That's the key difference, I would say. Here, head flit arbitrates. In circuit switching, there is no arbitration. Somebody already set up the path by doing all of that pre-configuration of resources. So there is similarity. I won't disagree that there's similarity, but it's a completely different model, right? In a sense. Yeah. There's basically, I would say there's no distinction between head, body, or tail in circuit switching, right? You just pump data, pump whatever you want to pump over there in the network, and hopefully destination figures out what's going on. Makes sense, right? Okay. If we don't have a class, I will finish something else. Okay. So basically, very quickly, I will finish this, and then we'll talk about interconnection network performance tomorrow and go to on-chip networks. So communicating buffer availability actually is also interesting. Right? Now you have buffers. Now we're complicating the network. You can communicate buffer availability. How do you do that is interesting. One is credit-based, the other is on and off, and the other is ACNAC. So it can have different signaling mechanisms between the routers. Credit-based means upstream knows how many buffers are downstream because you have some credits and you basically have that knowledge, maybe with some delay, right? Downstream router passes back credits to upstream. And if the upstream router has some credits, then it can send the packets. It knows that there's enough buffering and there's no problem if it sends the packet. Clearly, this leads to significant upstream signaling, especially for small flits. So there's a lot of communication between the routers just to communicate buffer availability, basically. This is not real. This is not real signaling. This is all overhead, right? If you think about it, this is not the data that you want to send. This is metadata about the buffer in which you're going to store the data. On and off is also interesting. Downstream has on and off signal to upstream. This is a bit less signaling because it basically says stop. I don't have any more buffers. As opposed to saying, oh, you have this much credit, this much credit, this much credit. Right? ACK is also interesting. Basically, upstream buffer optimistically sends the packet to the downstream, but it cannot deallocate this buffer until it receives an ACK or NAC signal. And clearly, this inefficiently utilises the buffer space, right? Actually, on and off also inefficiently utilizes buffer space as a rule. So let's take a look at credit-based. So this is node 2. It sends a flit, meaning a buffer becomes available over here. It sends a credit back to node 1. And it actually needs to send the credit to all of the nodes that it's connected to, right? Clearly. And then node 1 processes it, and then it sends a flit after some point, and then it also sends a credit back. And you keep doing that. So you can imagine the signaling right now. And then node 2 processes the flit. And there's a credit round trip delay in this particular case, right? So credit cannot be sent until this point. Yeah. Well, okay. So maybe we can go through this in the beginning of the next lecture. But there are different methods of signaling. They're not as important, but this is to show you the complexity of the buffering in existing networks. Okay. Any questions? All right, I'll see you tomorrow where we will start with interconnection network performance and on-chip networks.